Yeah, hello. Good evening, everyone. So this week we actually have a different programming strategy. Or rather, programming paradigm, as we call it, which we refer to as the divide and conquer algorithm. Sorry, divide and conquer strategy. So this is something that you would have actually seen in some earlier cases also, without actually realizing that this is indeed this programming paradigm. So the idea of divide and conquer algorithms is you have a given problem. Okay, so just give me a second. Let me share the screen. Yeah. So in the divide and conquer algorithm, right? So you have a problem. Okay. You divide this into sub problems. Okay. This might further get divided sub problems, right?
I
And
think
what
your
you
screen is not visible.
sorry?
If you are sharing something that is not visible, because
Who is
from
it?
your voice
No,
it is
visible. Visible. No, visible.
visible.
Yeah, it is visible.
Okay, let me check it out.
Yeah.
Reconnect it.
Okay. So here, one, two. Okay. So here again, you have these sub problems. You have divided into number of smaller sub problems. The interesting thing about these subproblems is that in the case of divide and conquer, we have disjoint subproblems, which means that if you divide into two separate parts, then there are no overlapping components or overlapping parts for the subproblems. So you can solve both subproblems independently. Say, for instance, you want to solve this one, you solve it independently. You solve this one independently, and then you have to merge the solution to get the solution of SP1. So what you do is you have a bigger problem and you are dividing it into smaller subproblems, right? So you have this problem again divided into smaller subproblems. Then you have to merge the solutions of the subproblem. You solve these things independently. You solve SSP11 independent from SSP12, and then whatever solution you get, you combine it and you give it as a solution for the SP1. Now you get solution for SP1, SP2, SP3, etc. You merge all of this and then you get a solution for the original problem. So this is the broad idea about divide and conquer strategy. You have a problem which, so it is not necessary that every problem that you find can be solved using divide and conquer strategy, because every problem may not be uh, it may not be dividable into subproblems which are disjoint in a sense. So this can only be applied to certain problems, and in this week, Sir's lectures has been focusing on some very typical examples where this strategy actually works. In fact, some of the algorithms that you've seen earlier, right? The binary search, the merge sort, the quick sort, all of these are actually are using divide and conquer strategies. So for instance, merge sort is a very typical example where you divide into two subhalves, sort them independently, merge it, and then you get a solution for a bigger subproblem, and then you combine the solution at that level, and then you merge the solution at the second level, and then you finally you do all the mergings, and finally you get the solution for the given input. That is, you get the sorted list for the given input. So this is the divide and conquer strategy. So without actually knowing you've been using that, you have indeed used it in many places. So in this week again, we look at some typical examples which are which are representative of the strategy, and which are quite easy to learn and analyze and try to understand. It also gives you different. So one is a problem in geometry, one is a problem in you know um, comparing rankings. So these are all like different problems from different domains, but the strategy can be applied independent of the domain, but the problem should be of a type where it can be divided into subproblems which are disjoint, which do not have any overlaps. Okay, so we'll come to the first problem, which is the inversions. So what inversions mean is that, say, suppose you have okay, I'll go to
Excuse me, ma'am.
yeah.
Ma'am, this divide and conquer code, have you explained it?
Sorry.
Ma'am, this code divide and conquer, inversions and merge count, have you just explained it?
Are you asking me if I've explained it?
Yes, ma'am. Yes, ma'am.
No, I've just started the session.
Okay.
No, I did not understand. Is that the question?
Yes, ma'am. Yes, ma'am.
Oh, sorry. Did you join late or something? Is that why you're asking?
Ma'am, I just joined. I just joined it now, so I was a
Okay.
bit late.
No, I'm just starting it. Yeah.
Okay.
Okay.
Okay. Thank you.
So inversions is like when you have, say, you want to compare your preferences for a certain thing, right? Say there is a social media post and you have given likes for it, and there is a different set of, or rather, I mean, when you say likes, you may be prioritizing something over the other, right? The example that sir has given is, say you want to rate movies, or in the case where you want to rate books, you have a certain ranking which you have in your mind. Okay, this is better than this is better than this is better than this, and you come up with a ranking, and then you want to compare with someone else's rankings. If these rankings are similar, what does it mean? So some person, say for instance, if there are, say, um, movie 1, movie 2, movie 3, movie 4, right? So there is this user 1, okay, who has rated like movie 2 is better than movie 4, is better than movie 1, is better than movie 3. And user 2 has rated it like movie 1 is better than movie 2, is better than movie 3, is better than movie 4. Okay. So what is the purpose? This is something called as recommender systems. Okay. So what the purpose of this is, suppose the likes of the user 1 and the user 2 are similar. So they are kind of appreciative of the same kind of movies. It means that whatever the user 1 is watching, right, that can as well be recommended to user 2. So if you see this, when if you observe like how you are given suggestions on the videos to watch, the ads to follow in the AdSense, right, the Google ads that you see, everything is kind of related to what you've been browsing, right? It is also possible that if you are in a network, say you are within the your college network or something, then you would probably all a number of people will be looking for the same thing, maybe during a given duration. Something like in this week I have PDSA exam, and there may be a lot of things which I'm searching on PDSA from a given set of given network, say given class of students or something. There is someone who has left the mic on. I think it's Nikhil. Nikhil, would you want to mute your mic? Yeah, thanks. Okay. Yeah. So if you want to, um, yeah. Okay. So the suggestions that you receive on this Google search page, the suggestions that you receive on YouTube, suggestions that you see on Facebook, all of these kind of make use of some advanced form of these recommender systems, where you like certain things, where you comment on certain things, which is in a way you are expressing your interest for that, right? So if you are, there are surveys also which happen, right? So based on that, you are actually given content which is similar to what you have seen. It's also possible that somebody in your network who has similar interests, maybe over a given period of time, also something like a week or a month or something, somebody has similar interests, and possible that you both are working on the same thing, or you both are interested in the same kind of things, and the recommendation that comes to you can possibly be recommended to other, or whatever you are watching can be recommended to the other person also. So it's not possible to recommend something which the other person will definitely like, right? There is no certainty. But these kind of rankings, this kind of recommender systems makes use of the pattern, some kind of pattern, and tries to find out the similarity between the likings of the two people, and then try to give recommendations based on these. Okay, so that is the core idea of recommender systems. So what is this inversion? So here if you see, okay, so as I said, user 1. So let me just, for ease of usage, let us just put these as like, I'm just going to represent it using simple numbers so that it is easier for us to apply this algorithm. Okay. So user 1 has said that M2, M4, M1 and M3, right? This is the order. Let me say that for me, M1 stands, 1 represents M2, 2 represents M4, 3 represents M1 and 4 represents M3. Okay. That mapping is done implicitly. So now once you get the solution, you just have to do a remapping. That's it. So this is the preference given by user. What? M2 stands for 1, M1 stands for M2, 2 stands for M4, 3 stands for M1, and 4 stands for M3, right? So this is the preference given by U1. Now if you see U2, what is M1 here? M1 is 3, right? This is what you have here, no? See, this is what you have here. So this is 3, right? And for M2, you have, this is 1. You're taking it from here, okay? Then for M3, you have 4, which is taken from here. And M4 is 2, right? So this is 3, 1, 4, and 2. So 3, 1, 4, and 2. So as you can see, this is another permutation of what the rankings given by U1. So the ranking given by U2 is just another permutation of the ranking given by U1. Now, if both of them had this pattern, right? If U2 also had this pattern, what does it mean? Both of them have similar lights. Suppose it was something like this, then both of them are totally dissimilar, right? What we want to do is, with the given ranking, we want to see what is the similarity factor. How are we going to do that? We are going to define a parameter which we refer to as the inversion. We say that ij, this pair ij, is an inversion if I is less than j, but j appears before I in this ranking. This is by default 1, 2, 3, 4, right? That is some mapping that we have given by default. That is anyway going to be 1 to n only, right? Whereas for U2, right? For U2, this is the inversion. This is what we are defining as an inversion. Inversion is a pair, this I comma j, where I is less than j, but j appears before I. What does it mean? Suppose you take this pair, say 3 comma 1, right? So I'm saying I is less than j. So in this pair, I put 1 comma 3 because 1 is less than 3, right? And this is I and this is j, and j appears before I. J is appearing before I in this. So this is indeed, this pair 1, 3 is indeed an inversion. What does that mean? This is a liking, or this is a preference which is not in accordance with the preference given by U1. For U1, 3 is anyway coming after 1 only because our sequence is like 1 to n. No? So U1 prefers 1 to 3. For U1, the movie which is represented by 1 is definitely a better favorite than the movie represented by 3. Whereas for U2, the movie represented by 3 is a better favorite than the movie represented by 1. So which is something like an inverse of what the U1 prefers. Therefore, we call such a pair as an inversion. Is this clear? Is the definition of inversion clear?
Yes, ma'am.
Okay.
Ma'am,
So,
re-explain that last thing, that 1, 3, why we are in
this example, this one 1, 3.
ma'am, 1
Yeah,
less.
yeah, you are asking me to explain 1, 3, right? Is it correct? Yeah. Okay.
Yeah, ma'am.
So see, we want to find all the pairs which are of this format, which means I is less than j. Okay, here I and j are there. I is less than j, but j appears before I, which means that it is opposite to the preference given by u1, because for u1 it is all in the increasing order, right? So if there is one place where this increasing order is not happening, that is an inversion. Correct? So if you look at the pair 1, 3, this satisfies this condition with respect to the ordering given here. Right? Because if you see 3, 1, 3, here I is 1 and J is 3. And J in this sequence is appearing before 1. Got it?
One doubt, ma'am.
Yeah.
This I will always belong to U1 and J to U2. So I
No,
U1 is
I and J both belong to U2.
okay.
I doesn't belong to U1. I never said that. It's not that.
Okay.
I and J both belong to U2 only. This is I, this is J.
Right.
I'm just defining inversion here. Okay. What is inversion is all what I'm defining.
Okay.
So 1, 3 is an inversion. Can you tell me any other inversion?
Ma'am, 4, 2.
Oh, yeah.
Yeah. No. So you have to specify it more clearly.
Ma'am, 4 is greater than 2, but it had appeared before 2.
Yeah. So it should be 2, 4, right? I said I is
Oh.
less than J, right?
Okay, ma'am.
Yeah. So such precision you have. I mean, I know what you meant, but precisely stating it is equally important. Okay. So
Okay.
I is less than J. So we say 2, 4 is an inversion. Okay. You are correct. 4 and 2 is an aberration. Like it is not in accordance with what I's rankings are, but still you just have to be more precise and you say 2, 4. So it is clear that 4 comes before 2 in this one.
Yes, ma'am. So, ma'am, we can say that U1 defines the regular ordering, that 1, 2, 3, 4, which is my ordering, suppose, and U2 is another person. And in U2, we have to check that is the ordering same as that, or it had appeared before something which was greater than, which should be appear before that as per ascending order, but it appeared before the smallest number.
Yes, there is a deviation from the ordering as it appeared in U1.
U1, yeah.
Which means that U2 has a different preference as compared to U1 with respect to these two values.
And that is called inversion.
Inversion, yes.
Okay, ma'am.
Okay, simple definition. Just get it, just look at 1 or 2 examples and it's very straightforward. There's nothing complicated about it. Okay. So our purpose to find the similarities, I am assuming everyone has got this. If you have to ask, please ask. If you put in the chat room, I may not see. Chat, I may not see it because I'm sharing a different window.
Ma'am, 2, 3 can be a pair or not?
2, 3 is in, yes. 2, 3 is also, it can be, it's a pair, of course, it's an inversion. Right? Because I is less than J and J 3 appears before 2. So 2, 3 is also an inversion. Okay. So now, can you tell me how many inversions are there here? Let me put it more clearly. 1, 2, 3, 4, 3, 1, 4, 2. Can you tell me how many inversions are there here?
One, 3, 2, 4.
No, I want the number.
3.
3. Is it? Everyone agrees on that?
Yes.
Yeah,
Yes,
3 only.
three,
Only
three
3.
only.
Only 3. Only 3.
Can someone list it? Somebody was listing it. I interrupted. Yeah. 1.
1, 3,
Mm.
2, 4,
Mm.
2, 3.
Okay. So 1, 2 is correct. 1, 4 is correct. 2, 4 is not correct. 2 is not correct. So 3, 4. Yeah. Okay. So these are the 3 inversions that we have, right? So can you tell me what is the maximum number of inversions possible?
n minus 1 by 2. So here it will be 6.
N into n minus 1 by 2. Can you tell me, can you explain why? Can you tell me in which one will that come? Which sequence will it come?
Ma'am, I think it would be 4, 3, 2, 1.
Yes.
Yeah. So which are the pairs here? If it's just 6, we can list it out. No? Can you tell me?
Ma'am, it will be 1, 4.
Oh, okay.
1 2,
Mm-hmm.
1 3,
Mm-hmm.
then 2 3,
Mm-hmm.
2 4,
Mm-hmm.
then 3 4.
Okay. Then
Ma'am,
yeah.
I think 6 has been completed.
Yeah. So as you can see, the number is n into n minus 1 by 2, which is O of n squared, right? Or rather, I would just say it is, yeah, order of n squared. Let us just put it in order. That's easier to understand. Okay. So this is clearly O of n squared. Okay. So if someone asks you to tell all the inversions, say you give me all the pairs of movies in which both the users differ, then what do you think is the minimum time that you need? Minimum time complexity, asymptotic time complexity.
Ma'am, I think it would be 0.
No. Minimum. Okay, so when I say minimum, I don't mean it. I mean something like a lower bound. At least, so for every input, or rather the specific case, right? So suppose you are asked to list all the, okay, let me just put it this way. It's not a lower one. It's a worst case. Okay. Yeah, worst case, what is the time that you need in the case of listing the inversions?
And square.
Sorry?
And square.
Yeah, O of n squared, right? Why? Because we have already seen that this is the maximum number of inversions that can come. So at least you need to list all of them, which will require an O of n squared. Is this clear to everyone? If you want to list the inversions, then you need at least O of n squared in the case when, in the worst case scenario, like you have this different order, right? So it is typically not like 4 squared, it is not 16, but we are talking in terms of asymptotic complexity. So here it is n into n minus 1 by 2. So it's O of n squared. So in the worst case, if you have to list all the inversions, it would still be O of n squared. So what are we trying to look in this algorithm? In this algorithm, we are just trying to get a count of all the inversions. In that case, can we do any better than n squared is the question. So for n, if you have to list all the inversions, the maximum number of inversions can be as bad as n into n minus 1 by 2, which is O of n squared, which means that you cannot do any better than that. But if you have to only give the number of inversions, right? Say you want to recommend a certain thing, but you will recommend it if the similarity is at least 70%. The similarity is 70%, then I'll recommend whatever user 1 is watching to user 2 also. So in such a case, you do not have to list the inversions, but you only have to get a count of the inversions. In that case, can you do any better? That's the question. Okay. So now what we do is, you have one, sorry. Okay, I'll just show you something that sir has given. So in the earlier case, it was 3, 1, 4, 2, I think. Okay. Now you draw a line like this. Now, wherever you see this intersections, right? The lines intersecting. This is the line intersecting 1, 1. This is the line intersecting 3, 3. This is the line intersecting 2. Line connecting 3, 3. This is 2, 2, and this is 4, 4. So you have this point which is intersection of 1, 3. You have this point which is intersection of 2, 3. And this is intersection of 2, 4, which are the inversions that you got. This is just for a pictorial representation and understanding of it. Okay. Now, coming to whether you can optimize if you only have to count the inversions. Okay. What we are doing here is, we will actually take this list, say 3, 1, 4, 2. Okay. We divide into 2. We find the number of inversions here and here, and then combine the solution for both. Recursively, we will further divide into 2, right? and then we combine the solutions for both. Does it sound similar in a way like whatever you did earlier? Some algorithm, yeah.
From merge sort.
Yeah, exactly. So what you're basically doing is you are actually splitting the 2 into half, 2 equal portions or almost equal portions in the case of odd numbered lists, right? And then once you sort each independently, you will merge these two to give the solution for this one and merge these two to give solution for this, right? And then you combine the solution to give the solution for the original problem. So this is exactly what you're doing in merge sort. But what does the merge mean here? The merge means here that whether you have any inversions that can happen between, say, suppose you have found the inversions here and you found the inversions here. What if there is an I here and a J here where I is greater than J? Right, so that will not be considered in the case when you are considering disjoint subproblems. These are disjoint subproblems, right? So that will not be considered. What if there is an I here and a J here and I is greater than J? In that case, this is an inversion that we have to catch in the merging. The merge process has to handle these inversions. So how does it do that? We follow the same algorithm as that in the case of merge sort. Now you have, say, 1, 4, 9, 2, 5 and 6. Suppose these are your subproblems at some say stage I or something. Now you want to combine the inversions of these two and you want to find whether there are inversions across. Say this is the left half and this is the right half. This half, okay, something like this half and this half. And this is an example where I want to show the merge. Here I cannot show it, so here I'm showing it. Okay, so first half now looks like this. It has been divided into subproblems and everything. Finally, you got the solution here. And now you want to merge these two. When you're merging these two, what happens is you take the first, what do you do in merge sort? You look at the list 1, right? You go through this loop, right? This loop, etc. If I equal to m, you append it to the second one. If j equal to n, you append it to the first one. If this is less than I, then you again append it to the, you append it to the same list, but you append from bj and then second list and then the first list. I hope you are comfortable with merge sort algorithm. I'm not going to that. Everything is okay, but finally this is one step which is different, as you can see. And this is also one parameter which is different from the merge sort. This is what gives the count of inversions. So initially we have set it to 0. What happens is, suppose this is your list, first list, and this is your second list. Okay. Now you're taking this one, you're putting it here. Now you want to see, you're going to put this one here, right? Because this is a smaller one. You're comparing this and this, right? And then you're going to put it here. What does this mean? Your list is now looking like this, right? The ranking list is now looking like this. Now, if you're going to put this one before this one, which means that there is a inversion of the form 2, 4 here. Is this clear? I have put 1 here, right? In the case of merge sort, now I will compare these two and I find that 2 is a smaller one. I have to put 2 here. What does it mean? It means that whatever comes after this is going to be bigger than 2, and all these values, whatever are here, are going to result in an inversion with respect to 2. Is this clear? Is this clear, or should I explain it again? You can tell me, like, it's probably not very intuitive in the first step, but I can explain it again if you want.
Ma'am, please explain it once more.
Yeah, I'll do that. 1 second. Let me clear it up once again. I have this. So at some intermediate step, you have these lists. Okay, 1, 4, 9, and 2, 6, 8. I don't remember what numbers I wrote. So what does this mean? This is the intermediate list like this, right? Something like this. This is not in, I mean, the inversion you have not done it, but in the case of merge, what you're doing, the merge, you actually look at 1, you put it here. Then you are comparing these two. These two is what you're comparing, right? And then you put 2 here in the case of merge method. What does that mean? My original list is something like this now. Even though I have divided into subproblems, my list is something like this. Which means that this 2, which should have come here if it was the same ranking as the other user, right? The user 1. In user 1, it would have been something like this is our assumption, right? If this was this is user 1 and this is user 2. User 2 is what I'm trying to merge. Now, if I'm taking 2 from here, which means that all the values which are coming in list 1 after this position are going to result in an inversion with respect to this value. Okay, let me explain it again.
So, ma'am, this second elif block is what you are doing with this. So you are
don't
first...
look at the code now. We'll come to the code. I'm just
Okay.
trying to explain the idea to you. Then we will come to the code.
Okay, okay.
Okay. Just try to understand in the case of merge, if you remember the merge. So this is, of course, I mean, if you want to look at the merge sort part of the code, you can look at it. What I'm saying is don't look at this part now. I will explain that. Okay, so if anybody is very comfortable with merge, do you want to explain the procedure? That will kind of, in your own terms, so that, it makes easy for us to understand what I'm trying to say. Okay, leave it, no problem. So, at least, are you clear that there is a possibility of some list like this and this list like this, which we want to merge?
Yes, ma'am. Clear.
Okay, so we are actually modifying the merge sort. Okay. Please remember that we're modifying the merge sort because we are using the same code as this, and only this line is different. So eventually, this will actually become 1, 3, 2, 4 because this part is getting sorted and this part is getting sorted, right? So let us look in this same case itself, 1, 3 and 2, 4. I put 1 here, then I take 2. But I know that I have not taken it from the left part, I've taken it from the right part, which means that there is a value on the right side which is smaller than 1 in the left side, which is resulting in an inversion.
Right.
Is that clear now?
Clear.
Yes,
So
ma'am.
whatever comes after this, after 3 will also result in inversion, like the list you showed before.
Yeah.
1, 4, 9. So 4, 9 is...
Correct, exactly. Whatever comes after 3, right? Because it will be larger. We are assuming that this part is sorted, right?
Yes.
So whatever comes after 3 will result in an inversion with respect to 2.
2, right.
Is this clear for others? It's not at all tricky, but maybe I'm not putting it right. So somebody wants to ask, you can ask again. Anyone has doubt? Maybe it's better to explain it just two values. So see, I have this 3, 1. I've divided into 3, 1 and 4, 2, right? What does merge sort do? Merge sort will sort this as 1, 3, 2, 4, right? And then do a merge of these two. So when it does a merge of these two, what does it do? It will first take this 1, put it here. Then it compares these two values, 2 and 3. If you know merge thoroughly, then only you will be able to understand this. I'm assuming you know the merge sort. Okay. Then we'll compare these two values. So the one on the right side is the smaller one, which I'm going to put here, which means that this value is larger than this one, right? So this is an I comma j pair as we explained for inversion. I is 2, j is 3, 2 is less than 3, but 3 occurs before 2. So this is an inversion.
So, ma'am, here you are trying to say that merge sort also is an example of inversion.
No. Merge sort is not an example of inversion. Merge sort, we are making use of the merge sort algorithm to count the inversions.
So, ma'am, but here 1 and 3 and 2 and 4 are the two lists, and here 3 occurs before 2.
Yeah.
And that's the thing that's a little part that inversion also tells us that if the value is greater than. So this is what I'm trying to say. So
don't say that merge sort helps. Merge sort is finding inversions. It is not. Merge sort is not
probably
finding
I'm wrong.
Yeah.
But what I want to say is that the idea behind that.
Yeah, so we are adapting or we are modifying the merge sort algorithm slightly to get the number of inversions. And this comes because, see, now let me tell you, suppose this list I've added say 1, 3, 6, 9, 10, etc. Okay. Now I have 2, 4, 12, 24, etc. I have put 1 here, I've put 2 here, which means that everything after this is going to result in an inversion with respect to 2. Is that clear?
Yes, ma'am.
Clear.
Clear, no? So this count 4 is a number of inversions that I'm going to get with 2. Got it, no? So I'm just getting the count of 4 in a single statement.
Okay, ma'am.
Okay,
Understood.
now that is the case which is shown here by saying m minus I. What is m? M is the n by 2.
Yes, the length of the first list.
Correct. Length of the first list, right? Minus I is the current position, right? This position, right?
Yes.
So this will actually give you the number of inversions caused by 2.
Okay.
Suppose you are taking from this element, it doesn't matter because there is no inversion. It means that everything here is kind of larger, smaller than this. So suppose you are taking 24. At some point you have written everything, you're taking 24. Because there is no element which you're taking from left, and because you're writing 24, you don't have to do this counting at all because there is nothing which is bigger than 24 in this one. So there is no inversion here at all. So for 24, you are not going to add anything to the inversion. You're only going to add these values for inversion. Say suppose now you come into 4. Okay, you wrote 2, you wrote 3. By 3 also there is no problem because everything that follows should be larger than whatever it is. That is totally fine. But when you're coming to 4 again, right? You're coming to 4 and you put 4 here, but there are still 3 elements here. So you're going to add that 4 plus 3, you're going to add to inversion because you're going to get the pairs 4, 6, 4, 9 and 4, 10 also.
So you are writing this 4 because there were 4 inversions with respect to 2 and 3 inversions with respect to 4.
Correct.
So that's what the count is here.
Correct. That is a number of inversions, right?
Okay.
2,
Yes.
3, 2, 6, 2, 9 and 2, 10, right? These are the inversions with respect to 2. As you can see in this list, 3, 2, this is an inversion. 6, 2, this is an inversion. 9, 2, inversion. 10, 2, inversion. 4,
Yes, ma'am.
6, 4, that is the 4, 6 pair is an inversion. 4, 9 pair is an inversion. 4, 10 pair is an inversion. And that's what I've listed here, right? This you are able to get it from the merge sort. See what a clever way of doing it, right?
Yes, ma'am. Understood.
So this is how you count the number of inversions using merge sort. Is this clear?
Yes, ma'am.
Anyone else needs help? Please feel free to ask because first time we are looking at this one. Is it okay?
Yes, ma'am. Clear.
Okay.
Ma'am, inside the code, please could you please scroll up a little bit?
Yeah.
Yeah. Ma'am, this thing, if I equals to m, which means I have come to the last element of this list A, and then I'm appending bj as it is.
Right.
Because both the lists are sorted in themselves.
And bj has only all the big elements,
All the big,
right?
yeah, okay.
And same
the
for j
next
equal
one,
to n. Yeah.
the next one is, I'm not clear about this. Could you please give an example for this LF part, j equals to n?
Yeah. So here you have, so what it means is that your B list is over, right? So you have say 1, 2, 3, 10, 12, 20. Okay. Here you have 4, 5, 6, 7, 8, and 9. Okay. Now you have 1, 2, 3, and you have written 1, 2, and 3 here, right? Now when you are writing 4, you have these 3 values. When you have 5, you have these 3. 6, you have 3. 7, everything is there. Now you wrote till 9, you have written here. Now your j equal to n, right? That's
Yes,
when
ma'am.
your j becomes n. All that you have to do is you have to append whatever is there in A to C, which is these 3. These are the ones remaining in A, right? This is the A and this is B.
So, ma'am, what is the meaning of A of I? A of I is one single element in A, no?
Yeah. So, no, I did not understand. What is it? Yeah, it's a single element.
Okay, so we are appending
You
one
will
by one.
increment it. Yeah, you'll increment it in this
Okay.
one. Again 11 will come, 12 will come, etc.
Okay, ma'am. I understood. Thank
Every
you.
time j equal to n only, right? We are not changing j in this loop at all.
Yeah, okay. Okay, ma'am.
So the case where you are appending this is none of these cases, right? So you are actually adding it from the, so a of I is less than bj. This is not correct. Your value is b of j is less than a of I. Correct? No, b of j is less than a of I is where you're going to do this counting. B of j is less than a of I. This is the condition, right? That's where you're going to count the inversions.
Right.
Yes, ma'am.
Is this clear for everyone? Is it okay? I don't hear too many yeses, so I'm a little
Yes, ma'am.
concerned. I
Yes,
hope
Clear.
you're
Clear, ma'am.
okay. Okay, yeah, sure. Thanks. Okay, fine. So this is the inversion. So now, let me just do.
They could.
Sorry. Okay, now do you want to tell me the complexity of the code? Okay, so you just note this, whatever count you're getting from left side, whatever count you're getting from right side, and whatever count you're getting while merging. That is the total count. Okay, so don't miss out this part. This is the answer for our solution. You're actually combining the solutions and whatever additional things. So we said now the left part has some inversions, right part has some inversions, and whatever are the cross inversions, right? Ij, where here is I greater than j situations. That is the count. That is a mergent. That's what we get from the mergent count. Okay. So that's something that you don't miss out. Okay. Now tell me, can anyone tell me the complexity of the code?
Be n log n.
Yeah, it's the same as merge sort, no? We have just added this one statement, right? It's a
Right.
simple, oh, this is O of one statement, right? You're just adding some number to some integer to another integer, right?
Yes,
It's an
ma'am.
O of one statement. So you're not adding anything to the complexity. It is simple O of n log n. Okay.
Ma'am, with this previous example, could you just explain it once? What is count of L, count of R, count of B?
Which one? These ones. See, I
Yes.
told you, right? So you have this big list. You are separating into two. You want to find the inversions in this part, and you want to find the inversions in this part. And then
Okay,
you want to
within
find the
themselves.
inversions that occur within themselves. Within themselves is nothing but you again go inside and split, you get again this. So whatever comes as this merging, that will come as the complexity for this one, right?
Okay.
This whatever merging is there, no, that will come as, sorry, not the complexity, the count for this one. That is simple.
Okay, so this was count L, whatever we did in n by 2 part.
So every time you split it, that will be count L. So here it is the count L for this one, but whatever you get from this count B, right? This count B, whatever, not count L plus count R plus count L plus count R plus count B for this one will be the count L for this one.
Okay. And ma'am, what will be the count B here?
So that is what is the count? Okay, let me just put it. So this is some confusion everyone will have when you try to combine the solutions. Okay, see, you have a problem. Okay, you're splitting it into two. Okay, so this is one smaller problem and this is another smaller problem, right? Then you are splitting it into further. So this again you're splitting into two, right? Now, suppose this is of length one each. Okay. Now you have a count B for this. What is count B? What you get from merge, the merge method, right? In the merge sort, you remember the merge method. You had an O of n, remember?
Yes, ma'am.
When you're merging, you have an O of n, right? Because you're going through both lists and generating this new list C, remember? That is an O of n complexity, the merge method. So just like that, this count, the count that comes from here, there are no inversions because it's only one value. Here, there are no inversions. But when you combine this, suppose this was 2 and this was 1. then you have one inversion, which is this. So this gets added to, this will be the count L.
So
The
ma'am,
count L of, yeah.
yeah, ma'am, the count B here for 1 and 2 is the is this inversion during the merge.
Merge, correct.
Okay, I understood now the count.
Now the count L is what comes from here. This count L plus count R plus count B of this level, right? That is a count L for this one. There is a count L, count R, and a count B for this part. That will be the count R for this problem. And this itself has a count B. Now this sum of whole thing will be the count L for this problem.
Okay, ma'am.
Is it clear?
Yes, ma'am, it's clear now.
Okay. I hope it's clear for everyone. Unless you ask, I will not be able to understand. I'm assuming people are understanding. Okay. So this is the complexity is just that of merge sort. There is nothing different that we are doing except adding one O of one statement, which is a very clever way of. So as I told you right now, if you have to list the inversions, we cannot use it because here in this statement, we are using a single statement to cover number of inversions together, right? So here we said that this 4, instead of listing all these, we are just taking this number 4, which is kind of a, which otherwise would have resulted in an O of n. Here it is an O of 1 only because you are just taking the count, which is 4. And the second one, you are just taking the count 3. So for 2, you're getting the count 4. For 4, you're getting the count 3. But if you had to list these, then each of these would have been an O of n, and that would have resulted in O of n squared. But because in this step, right, we are not listing the inversions and we are only taking the count by which we are addressing a chunk of inversions in a single go, right? That is why this is resulting in an O of 1 and it doesn't have an O of n. That's why it's actually giving an O of n log n. If we had to list the inversions and if we had gotten the reverse order, then necessarily this would have been an O of n squared. Okay. Fine. So is it
So
clear
this,
for everyone?
yeah, ma'am. So this practically, how does it? I mean, like you have higher the inversions, the more dissimilar these in the recommendation system.
No. The more they are similar, the more you will recommend. In the sense that you assume that they are similar.
Yeah. So higher inversion is more dissimilar.
Correct. Dissimilarity. Correct.
Yeah. So okay. So and then finally, how does it get into converted into like that percentage?
See, you have okay. So you say that if they are similar by say all the pairs, right? So that is something like n squared, no? Out of that,
Right.
if they are only similar by say n, I mean something like that, some percentage like that. I was just
yeah, all
giving you
similar would be in
example.
like a 100% match.
Correct,
So
100% match. Yeah. So this will be
Okay.
something like a n by n squared or something like that. Whatever. I don't know. I'm just telling you something big. Just give you an idea about how we can make use of it. There may be so many other ways. Just doesn't have to be a percentage counted down. But similarity, finding similarity as a number, right? That actually gives us an idea about whether the likes and dislikes of these people are similar and whether they can be recommended the same advertisement or same video or whatever, right? So that kind of helps.
Okay.
Of course, in real life, these algorithms are much more complicated, but this just giving you an idea, some very basic components put together will give. But these are like very beautiful algorithms. You already have a merge sort algorithm which you would never have imagined that you can use it for in counting inversion. So it's a beautiful way to do that, and that's why these algorithms are introduced.
But these machine learning algorithms can also be used for measuring similarities, right?
Yeah, I mean, I'm really new to machine learning, so I really cannot comment on that. I guess you people should do that. I mean, if you already done a diploma on that, please feel free to think about. Maybe you can ask the ML instructors. I don't want to speak anything which I have no idea about. So,
right, ma'am.
Okay, yeah, sure. Okay, sure. So we go to the next problem, which is closest pair. Okay. So here again, we start off with one. Okay, I just. Here again, we start off with some problem that Sir had introduced earlier, which is in a video game, right? So you have on the screen you have number of objects, and you want to find the closest pair of objects which are closest to each other. So if you want to find a pair of objects which are closest to each other, what is the immediate algorithm that comes to your mind? Could be naive, it could be advanced or whatever. Like what comes to your mind immediately?
The,
Ma'am, the Dijkstra algorithm.
How does Dijkstra help you?
Hmm. I don't think, ma'am. I just
No,
thought that
I mean,
maybe.
no, you can think about it. There is nothing wrong in that. You can actually think about it, but
Line or a line out of 2 points.
line, sorry.
A line for 2 points.
Yeah, and
A line joining 2 points.
no, I'm saying like, okay, so these are all points on the two-dimensional plane. Okay, you have an
Yeah.
x coordinate, you have a y coordinate, and you want to find the pair which is closest. So, who suggested Dijkstra? See, Dijkstra
so we can
actually.
measure.
Sorry.
You want to find which is the closest pair is by finding the distance.
Distance, correct. Yeah, the Euclidean
Right? Yeah,
distance.
so that will be you can use the a square. I mean c square is equal to a square plus b square. For
Yeah.
that.
Yeah, correct. So that is finding the distance between 2 points, right? I'm asking what is
Right.
the shortest minimum distance? How do you find the minimum distance? In the sense that you give me any 2 points, the distance
Between
between
each
them
point.
will be the smallest among all pairs of points.
All right.
How do you find that? Can you suggest a naive algorithm? I mean, if you have an advanced thinking,
You'll have to naive algorithm would be to take one point and find the distance between each.
correct. You go for all possible
Go
pairs,
through
right?
the all possible pairs, right?
Yeah.
Right.
So that is clearly not an efficient solution. So here, again, we make use of this divide and conquer. Okay. So in the case of earlier case, we saw that the merge sort, right, which is a divide and conquer, actually improved the algorithm from O of n squared to O of n log n in case you only want to find the number of inversions. So here again, this closest pair example, right? So we do some such similar, what do you say, some such improvement.
Excuse me, ma'am.
Yeah.
Ma'am, for Dijkstra, I thought that if there's a point, suppose it named P, and we have to find the closest pair from closest point to the P, so that we could get the closest pair P comma some point. So therefore, I thought that Dijkstra may help. Could you please suggest me that where I was wrong in that?
So there is a graph here.
Yeah.
No, that's okay. I mean, your thought process is totally fine, but I'm just asking. You can come in. There is a way to do that. You can tell me. Like, I'm not discouraging you. I'm not saying there is no graph. You cannot do that. I'm asking you to think. Like, can you think
Ma'am,
about a graph?
directly it is there is no graph because these are just the points scattered along this.
So, but you can think about a complete graph, right, between every pair of points, and then can
Yes,
you
ma'am.
find the Dijkstra? Then you run the Dijkstras and find the smallest path. Sorry, the
That's
smallest pair.
That's what Mama suggested about.
See, Dijkstra is actually finding you the shortest path from one vertex to another via a number of vertices, right? Here, that is not what you're looking at.
Because we are
See,
looking
for
at the
instance,
distance.
here, yeah, for instance, here, there could be a path from this to this to this to this to this, right? But you are actually looking at the shortest Euclidean distance, which is the shortest path. This
Okay.
path. No? So, in the case of Dijkstra, if you have an edge between every pair of vertex, then what is the shortest path?
So, ma'am, here the conflicting thing is the number of vertices and the Euclidean distance. Because we
No.
want
Hold on 1 second. So, if you assume that the distance between every pair is the Euclidean distance,
Yeah.
right? Then it is the edge weight of that, the Euclidean distance is the edge weight of that edge connecting two points, right?
Yes, ma'am.
You got it now? I mean, that way you can actually find the minimum distance. But what you need is the minimum among all possible pairs. So it's more like all pairs shortest path than Dijkstra single source shortest path.
Okay.
Because you are just starting from one point. That may not be the pair in that pair at all, right?
Okay, so we do Dijkstra is something single source shortest path, and we want all pairs shortest path.
No. I'm not saying like you can do the all pair shortest path or anything. But why doesn't Dijkstra work is the example I'm trying to tell you. See, Dijkstra, you are given a source. Here there is no source. You have to find both the source and the two endpoints of the distance which is the shortest. You do
Okay, so
not have a source to start with.
no point is fixed. Like suppose in the source vertex, we were given that we have to start the Dijkstra algorithm from vertex node 1, suppose, but it's not something similar to that here in this
Yes,
case.
we don't have such a source.
Okay.
We have to find the minimum distance between a pair, which is the shortest distance among all pairs possible.
Okay,
So
ma'am.
we are
I
not given a
understood.
source. Okay. You can think about in terms of all pair shortest path, and we have seen that all pair shortest path has this lower bound rate. I mean, you cannot do better than that and all that. But here it is a totally different kind of a scenario. So for now, yeah, I mean, you can think about like graphs are something that comes intuitive to many people. Like when you're trying to solve a problem, a lot of things. But even though many real life problems can be solved as modeled and solved as graph problems, it may not be the case with all the problems. Okay. Yeah, but think about it. If something occurs to you, something interesting occurs to you, just feel free to discuss. Okay.
Okay, ma'am. Sure.
Okay, yeah, sure. So, yeah. So now what are we going to do with the shortest path, right? So you have a set of points which are scattered on the plane. Okay. Now okay, these are all supposed to be points. Sorry about that. Yeah. So what are we going to do is we're going to divide this into equal parts where the left half and the right half both have equal number of points. And then we find the shortest path in this part and the shortest path in this part. Sorry, shortest distance in this left part and the shortest path distance in this part. We check whether they are shortest, and then we combine the solution. When we combine the solution, there could be some path like this, which could be a shorter distance as compared to what we have. I have to start. I think I'll show it. Okay, this is the shortest here. Okay, and this is the shortest here. So this is of length say 2, this is of length say 3, and this is of length say 1. Now you have found out this is the shortest here, this is the shortest here, and when you combine the solution, you have to look at all the points in this area also, right? Whatever could be going with from this. I'm really sorry, I'm not able to draw straight line. Just let me get it straight 1 second. I'm just drawing, okay, maybe horizontal line. I'll just discard. So I have a set of points here. This is the shortest distance here, and this is the shortest distance here. But there is something which is even shorter here. Okay, so this is say 2, and this is 3, and this is 1. Okay. Now, how we are going to use this divide and conquer algorithm is, say you have a set of points P. You find something which is there on the left hand side. You find something there on the right hand side. You solve the subproblem on the left hand side. You solve the problem on the solve the problem on the right hand side, and then you combine the solution to get a solution for the bigger problem. That is the idea. Now, what are the challenges here, right? So first of all, what we do is we want to find a way in which we organize these points. So we want to find a way in which we want to process these points. So for that, we do two levels of sorting. One is we list these points in the increasing order of x coordinate, and we list the points also in the increasing order of the y coordinate. So suppose your points are something like 2, 5, 3, 4, 1, 6. Then the p of x ordering, right? That will be something like 1, 6, 2, 5, and 3, 4. Whereas your py will be something like 3, 4, 2, 5, and 1, 6. Is this clear? Px, py.
Clear.
It is sorted. Yeah, it is sorted based on x coordinate. Here, this is sorted based on the y coordinate. Okay. This is the px and py. So we have this listing. Now we want to further partition this into left and right. Right? How do you do this partitioning? You look at the points which are in the middle, whatever you have drawn, and whatever are there on the left, smaller than whichever have the smaller x coordinate than this, you will put it on the left portion. Whatever have the higher, bigger x coordinate, you will put into this portion. But when you do this partitioning, see, now you have a problem which has px and py, suppose. Or sorry, not px and py. What is the name of that? Yeah, q and r. Okay. This is what is given in the lectures, and that's why I'm just sticking to that, so it avoids your confusion. Okay. So you have something on left which is q and the right which is r. Now this problem, right? This also you have to have the qx and qy for this, right? If you want to divide into smaller problems, you need to have the qx and qy. Where I'm using the qx and qy, I will show it to you when we see the code. Sorry, rx and ry. Okay. How we do this is x coordinate. You can actually do it from the left to right. You can do a simple scan, and whatever comes before this middle line, right, that you put it into qx. Whatever comes in the whatever is greater than x, you will put it in the rx. Qy, this is already, there is already a sorted order in py, right? Here you will look at the x coordinate, and whatever comes to the left of this, you will put it in qy. Whatever comes to the right of that, say suppose 3 is the point here. Say this is 3. 3 is the x coordinate here. This is the x axis, right? So this is the point, say 3, 0. This is the point here. Then whatever is coming to the left, say 2, 5 will go to qy because qy is the left one, and 1, 6 will go to ry. So this is the partitioning that we do. This is how the recursive. So why we need this recursive subproblem is whenever we are using the divide and conquer strategy and we have subproblems, right? The subproblem should have the same structure as that of the original problem. So we say we have a p which we have divided into px, not divided into, we have given a different presentation which is px and py, which are two different sorted lists of the points in p based on the x and y coordinates respectively. And then we partition it into q and r based on whatever falls onto the left of that midpoint that we have identified and whatever on the right side. Now, if you want to find the qx and qy for this, we do this separation because we also need a qx and qy for the subproblem, which is a q. Otherwise, if the subproblem does not have the same structure as the given problem, you cannot work on it. The size of the subproblem may be different. In divide and conquer, in the case of quicksort, you would have seen that 1/3 and 2/3, right? So one portion is 1/3, the other is, that's also a divide and conquer. But the size of the subproblem may not be the same there. It could be 1/3, the other is 2/3. But the structure of the subproblem should be the same as that, which is that of the main problem. So if you're losing me out on certain things which I'm telling you right now, it is okay. These are not like really important, but yeah.
I have a doubt, man. I'm
Yeah.
not understanding how did you partition this px and py or the
Yes, ma'am,
2,
this is
5,
partition.
No, px and py is not partition. Px and py is this list.
is a representation in a different manner.
Yeah, it is just sorted points.
Yeah. So how we partitioned this 2, 5, 3, 4, and 1, 6? How are we putting in left and right?
I'm just identifying one point which will give me half the points on left side and half the points on right side. Half the points coming on left side will be my q, half the points coming to the right of that x will be r. I just identify one point like that. That's it.
Okay. Okay.
And the y
partitioning also? Can you please explain?
Yeah, why partitioning is like you cannot directly do a scan, because see, if you directly start doing from here to y, right, some will be on the left side, some will be on the right side, so it is not directly possible for you to put it in either in qy or ry. So what you do is you look at the py and you start from the smaller value, say. So you have 4, the 4 will, this 3 4 will come first, 2 5 will come here, 1 6 will come here, like this, no? Because this is the y coordinate, right? This is the 6 y coordinate, this is the 5 y coordinate, this is the 4 y coordinate. Now you are seeing, okay, this is our 3 4, suppose this is our 2 5. I'm just telling you, okay, you can just assume whatever later you, okay, this may not be 3 4 because here is your 3 0. So ideally, okay, the idea is py, you take the first one, you see the x coordinate. If it falls to the left of the partitioning line that you have identified, then you put it in qy. So this will go to, okay, so this 3 probably was a bad choice. I will put it as 3.5 because whatever line you are partitioning, that will not go through any point. Okay, that will be like a middle line which will partition the points into correct 2 halves, right? So that will have a different x coordinate. So if you have, say, 3 which will come on the left side, so say 3 5 3 4 will be somewhere here. So that will be put into qy. Now you're coming to 2 5. 2 5 5 is actually here, but 2, as you can see, is again coming on the left side of
So all the 3 in QI in this case, correct?
yeah, so that's a bit of a confusion, right? So you want to partition. So if you put 3.5, what happens is it's actually all the points are on the left side, right? So our
Yeah,
partitioning is not
2.5.
correct. You cannot have 3.5. You should have something like 2.5. Okay, this is the 2.5 x coordinate. Okay, I'll do it again clearly. Sorry about this mess.
Ma'am, here the P is divided into 2 parts, that is Q and R.
P is a set of points and P is divided into 2.
Ma'am, what is PX and PY then?
Px and Py I have written here. No, that is actually a sorting of the points, a listing of those points. 1 second, I will show you. Okay, just give me a minute.
Okay.
So, okay, suppose this is your 2.5 comma 0 on the number line. So you have your 2 is the x coordinate, right? So 2 will be here and 5 will be. So this is your 4, this is your 5, it's your 6 in y coordinate. So your 3 will be somewhere here, 3 comma 0 will be here. Your 2 will be somewhere here, 2 comma 0 will be here, 1 comma 0 will be here, assume, okay? This is your, so here you have 2 comma 5, so this is your 2 comma 5. And 3 comma 4 or something here, 3 comma 4. Right? And 1 comma 6 is here, 1 comma 6 is here, okay? Now, Px is a listing, so this is P, set of points, okay? P is a set of points on the plane, right? Is it correct? The input points.
Yes.
1 second. So you can see in this code, no, this PTS is what we've shown. This is a set of points, the list of points, right, on the plane. Now this P, we are going to list it in a different way. One is the sorted list based on the x coordinate, and the other is the sorted list based on y coordinate. Is it clear? It is not a partitioning of points at all. It is just another listing of the points in P in a different order.
So ma'am, here Px is 1 comma 6, 2 comma 5, 3 comma 4 means that 1 comma 6 is the closest among all.
No, nothing like that. We are
Okay.
just coming up with a sorted order of just a listing of P and F. There is nothing like we have not even started computing the shortest distance.
Okay, so with respect to x and y is what you are listed here as px and py.
Yeah, I have, this is the sorted order, like 1, 2, 3, right? Sorted based on x coordinate. This is sorted based on y coordinate. Sorry, this is y.
Okay.
This is x. Okay. Now, I'm going to divide it into q and r. So I don't have q and r right now, right? I am showing it pictorially here. Doesn't mean q and r is created, right? I have to create it using the code. So how do I do that is what I'm saying. So q and r, I have identified a point which will divide into equal number of points. See, if I had another, say,
You are considering only px right now, ma'am, na? Only px.
no, what do you mean by that? Sorry.
You are considering the point px only, na? 1, 6, 2, 5 and 3, 4. px,
Where? Considering where?
This considering points 1, 6, 2, 5 and 3, 4.
No.
This is px only, na?
No, I like, just one second. I'll explain it again. Just give me a second. 4, 4 point. I'm adding it so that it becomes equally distributed. Okay, that's why I'm adding it here. So now I have 2 points. So how I want to partition is I want to draw a line such that I have equal number of points on this side and equal number of points on the right hand side. Okay. Now for that I draw a line which is a 2.5. Okay. Now P is the list of points which is given to me. That can be given in any order. It doesn't have to be an order of X, order of Y or anything. It's just given something like that. I am actually generating another list which will be sorted based on the X coordinate of points in this P. Which are the X coordinates? 2, 3, 1 and 4. If I sort this list P based on the X coordinate, I will get 1, 6, 2, 5, 3, 4 and 4, 4, 5, right? And that is exactly what I've written here. I've not done anything fancy. I've just rewritten the list here in a sorted manner based on the X coordinate of the points in P. That's it. Py is the list. I can write it neatly. Py is the list which is sorted. I'm sorting P based on the Y coordinate. So here I have 3, 4 which is the first point. Then I have 4, 4.5 which is the second point. 2, 5 which is the third point and 1, 6 which is the fourth point. So this is another listing of the points in P. That's it. There is no partitioning here. The partitioning, what I'm going to do is P is going to be partitioned to Q and R. Px and Py are not partitioning. Px and Py are just another listing of points in P based on the sorted order of X and Y coordinates respectively. Okay. Is it okay? Px and Py? There is no partitioning.
Yes,
it's just another listing. Okay. Partitioning of Q and R. Actually, you are finding a point somewhere midpoint here, and you're putting all the points that come to the left. All the points which have X coordinate less than this one, right? This midpoint, you will put it here. All the points that you have greater than X coordinate, which is greater than this one, you will put it here on the R. Now, just like you had, so now what is your Q? Your Q is 1, 6 and 2, 5. Your R is 3, 4 and 4, 4.5, right? This is your R. Now, just like you did for Px and Py, you want to find the Qx and Qy. And because you do not want to do a sorting, the simple thing to do is you just do a scanning of Px. You do a scanning, you find that until here it is less than 2.5. So you simply put 1, 6 and 2, 5 here, that is sorted based on X coordinate. And for Y coordinate, what you do is you scan from this to here, and whatever is less than 2, you put it into Ry, and sorry, whatever is less than, you put into Qy, the other one you put into Ry. Is that clear? Okay,
So
you go
ma'am,
to yeah.
to summarize all the things here, we have P points, a P set of points, and Px is something the points have been ordered because of these x coordinates with respect to the x coordinates, and Py is something the points are ordered with respect to the y coordinates, and Q and R are the partitions. Suppose we are say the Q is left of 2.5, that is the partitioning x coordinate, and R is something right of this partitioning point 2.5, and this thing is all about which you have just explained.
Q and R are partition based on x coordinates, but Q and R have nothing to do with. I mean, Qx and Qy. Okay, Q and R is a partition of P. You are partitioning the points in P into Q and R. Px and Py are not partition; it is just an order. Q and R are partitions of P based on a certain constraint. Now, because you are dividing it into subproblems Q and R should also have the same structure as P. So you should also have a list which is Px and Py again here. I mean, similar to Px and Py, you should have Qx and Qy. You can very well sort it, there is no problem. But again, if you
And
want to
Q,
avoid the sorting,
So this is the recursion thing here, no? Like similar to this P, Q has been taken, and Px and Py, and similar to this Px and Py, Qx and Qy has been taken, and the similar process is repeating till this.
correct. That's it. It's for recursion. To enable recursion, you should have a subproblem which has the same structure as your original problem. That's it.
then
Okay, ma'am.
QI will be 5, 2, and 6, 1. QI
Qy will be
5, 2, and 6, 1.
It's 2, 5. 2, 5,
2,
and
5, and 1, 6.
the points won't change, but will be sorted according to y coordinate.
yeah. This will
Yeah,
be
2,
the
5.
sort.
Yeah. 2, 5. 2, 5, and 1, 6. Yeah.
Right.
Yeah, okay.
Okay, so we have not actually gone to the main matter of the problem yet. So let us come to that. Okay. So here, if you want to look at the sorting of, just like I told you in the earlier case, right? You find the count of L, count of R, and then count of B. That gives you the total count, right? So here, you're actually going to find the shortest pair in the, or sorry, the minimum distance in the left side. Then you find the minimum distance in the right side. Then you want to see whether there is any minimum distance which is smaller than what you found on either side, which comes in the overlapping area, which is crossing that middle line. Right? So here I told you, right, if there is anything here, that is what we want to figure out. Okay, so for that I show you another example, another figure. Okay, so this is the line which I drew, the middle line. Now I have a set of points on the left. This is my Q side and this is my R side. Now, suppose you have found a delta somewhere here. Okay, what is delta? I will tell you. This is one is here, and this is something which is something like this. Okay. Now this is the shortest distance on this part, say delta 1, and this is the shortest distance on this part, which is delta 2, and I find that delta 1 is less than delta 2, so I say that delta equal to delta 1. That is minimum of the shortest distance between L and R. That's it. Whatever is Q and R. Whatever minimum I got from Q, I'm indicating it as delta 1. Whatever minimum I got from the right hand side, I'm indicating it as delta 2. And delta is the minimum of delta 1 and delta 2, which means that that is the shortest path, which is shortest distance which I've got from both combined, without looking at if there are any things that cross this boundary. Okay. Now what I have to do is I have to see whether there are any pair of points which will cross the boundary which has a distance, say delta dash, which is less than delta. Is this clear? That is my combining the subproblem, right? Combining the solutions of the subproblem amounts to finding if there is any pair which crosses this this line, that middle line, and the distance between which is smaller than this delta which I have got. Is this clear?
Yeah.
Got it? No? So our aim is to find if there is such delta. What if you have everything here which is smaller than delta, right? I mean, this is the worst case scenario, right? I mean, you have everything here which is smaller than delta possibly, right? Something like this, right? Everything here which is lesser than delta, suppose. For that, we show that that is actually not necessarily the case. That will be something which is in a manageable number of values which will only cross this, is what we are trying to show. So I've already told you delta is less than or delta is equal to min of delta 1 comma delta 2, where delta 1 comes from Q and delta 2 comes from R. Okay. Now what I want to see is, so this, suppose this is my delta. I'm saying I'm going to look at the portion which is to the left of this and to the right of this at delta distance. What is the advantage of that? Any point which goes beyond this delta, right? This will be at a distance something like this, and we are not worried about that because that will be at least 2 delta, right? And definitely I've got something which is smaller, so I don't even have to worry about such points. I only have to worry about points which are within a distance of delta from the middle line. All other points which are outside the delta, I do not have to worry about it, because if there is some pair that is something like this, it will definitely have a length which is at least 2 delta, because this is the delta, right? You can see that now I'm only looking at this band which is delta at a delta distance from this middle line. I only have to look at all the points which lie like this, right? So I'm totally going to ignore the points of this type. I only have to worry about the points which are of what type? This type, right? Something like this or something like this. So this could also be less than delta, right? Because this is what is delta. So this could also be.
So, ma'am, the line joining the point should cut this red line.
Yeah, but because other part we have already solved, no? The ones which are contained totally within Q and the ones which are totally contained within R, we have looked at all of them and we have come up with the delta 1 and delta 2 and found the minimum among the two. So we only have to worry about the points whose connecting line will cross this partition.
Okay.
Is it clear, everyone?
Yes.
Why are we considering only these lines that cross this red line? Is it clear for everyone?
Yes, ma'am.
Yes, ma'am.
So is there any reason, ma'am, why we are taking this 2 delta window? Means we can
we can have something like this, no? Okay, sorry, what was your next question?
My question is why we are taking this 2 delta width window?
What should we have taken?
We take delta window because anyway we have to find the distance. The closest pair which is less than, which is having a distance between them less than.
So you mean delta? That is, we should have considered only this. Is what you mean, not this one? Is this what you mean?
Yes.
So how about this one? What about a line like this? This is less than delta, right? I mean, this is possibly less than delta, no? Because it's starting before. See, this is what delta is, right? This is delta. So a line which is coming from here to here can be less than delta.
Ma'am, I am not able to see your pointer.
Okay, one second.
Yeah.
Suppose I have a point here, okay, which is outside the delta by half. You are saying like this is the window that we should consider, right?
Okay.
Now this point is here and this is here. What is the length of that?
The length of is less than delta. Yeah.
So does it answer your question?
Yes. Okay.
Yeah. So that is why we are considering this 2 delta. Okay, delta to the left and delta to the right. There could be points, something like that. So, yeah. So now we want to figure out if there are Now, what we are trying to say is that we cannot have something of this form. Like there cannot be so many things which are at something like this. This is what we are trying to say. Okay. Why? So let us see. Suppose there are 2 points. Say one is so look at this particular cube. Okay. Sorry, the square. Suppose you have a point which is here. If you have another point which is here within this same point, is it possible? Is it possible to have 2 points like this?
No.
No,
Why?
because it will be
Delta is the minimum distance already.
delta by root 2.
Delta is the minimum distance when it comes to this part, right?
Yes.
And how about the same way for the other side also, right? We cannot have such a point, right?
Yes.
So every square can contain at most 1 point. Is this clear?
I'm not getting. Can you repeat that? The diagonalized point?
This, suppose, can you have a one second. Yeah. Can you have a point? Can you have 2 points which are so you have a point here and you have a point here. Is this possible? From whatever we have concluded and assumed so far, is it possible to have 2 points like this?
Not possible. Not possible.
Why?
At least.
So what is the distance between these points? What is the distance between these points? See, this is delta by 2. This is delta by 2. Is this
Delta
clear?
by root 2.
Yeah. So delta by 2 the whole square plus delta by 2 the whole square. This is the distance between these two.
Yeah.
Which is delta by root 2. And root 2 is 1.4 something. So this is strictly, this delta by root 2 is strictly less than delta. Is this correct?
Yeah.
But our assumption that there cannot be a point which is, okay, maybe the point should not be touching the red line. It is just here. Okay.
Yeah.
In that case, we cannot have a line, we cannot have a distance which is less than delta because our assumption is that delta is the smallest distance inside the Q section, right?
Okay. Thanks.
So we cannot have 2 points inside the same square. Is it clear?
Yeah.
Okay. Now, in that case, how many points? Say, suppose my point is here. How many points do I have to compare?
2 points.
See, suppose something is here, then the worst distance that it can go to is something like this here, right? I think this would be delta, right? So I cannot go beyond this. Okay, I'm not making sense here.
Cursor is not visible.
No, hold on 1 second. Let me just.
Okay.
See, you have a point here. Okay. Now, what are the squares in which you can have a point such that it will be less than delta? So it could be, this point could be here, this point could be here, this point could be here, this point could be here. Let us look the worst case. Like from here, the farthest square that it can go to is something like this. Beyond which, if it goes, it will become delta. Is it clear? No? Let me explain again.
Yes.
See, suppose you have a point here. By the time it reaches here, it has already covered delta by 2. It reaches here, it has covered delta. Am I making sense?
Yes, ma'am.
Yes, you can't go beyond this, right?
Yeah. So even if you are in the worst case on the borders of these squares, right, you cannot go more than 3 rows. 1, 2, 3. Maximum you can go is these 3 rows until
Correct.
here. I mean, worst case.
Ma'am, but minimum is only constrained, right? If it is more than delta, what is the problem?
No, more than delta we don't consider at all. What I'm saying is,
Okay, well, no
you
need
have
to
a
consider
point.
since it is more than delta.
Yeah.
Okay.
What are the points that I have to consider? I'm saying
Okay.
that you cannot have a pathological scenario like there are so many things that you have to compare. I'm saying it is a manageable number is what I'm trying to say.
Within
The
whichever
number
comes
of
within
points which you have to
delta.
compare. Yes.
Okay.
So suppose you have a point anywhere on this square, the worst that it has to compare is some point inside the square or in this square for that matter. Worst case. So if I number these as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, right? So why 16? Because this is going beyond this. So this anyway we don't have to consider because that will 1 to 13 we don't have to. Okay, 1 to 13 anyway we don't have to consider because we know that it cannot be more than delta. So if you have say 1 to 16, okay, 1 to 13 does not have to be considered only if it is here, but only if it is here. Otherwise, if it is here, you might still have to consider. That's a different thing. So the point is, if you are looking at a point inside the square 1, you have to compare it only with another 15 points. Maximum of 15 points is all that you have to compare.
Should we consider both the direction, like if something is there below 1, 2 rows?
Towards the last one.
If 9 is the point.
So that's why we have actually sorted the points, no, from P by. So we are actually starting from the smallest point, right?
Okay. Okay.
So that is why we have the sorted order in that P y, Q y, R y, and all that, right? So we start from the smallest point on the y coordinate, so that we only have to look the ones which are above.
Okay.
And whatever is there, that will be covered here. And when I'm looking at 5, I don't have to look at whatever is there from 1 to 3, 1 to 4, but that I've already considered, no? So I will only look at points from 5, 6, 7, 8, and then here 17, 18, 19, 20. This is all I will consider. So that is why that sorting is required. The P by, right?
Yeah, okay. Got it.
You start from the smallest y coordinate. You look everything that is above. You consider the 16 squares. Only you have to compare there. You finish this row. You go to the next row. You compare the next 4 rows. So the idea that we are trying to put across is that you are not comparing any random, like any n number. If it is not a function of n, when it is a constant, you are able to reduce it to of n squared factor. That is what I'm trying to arrive at. You only have to compare with a constant number of points or something smaller than that. See, suppose you have only said 6 points in that whole band, then you don't even have to compare 15, no? You only have to compare something which is less than that. So the bound, the number of points that you have to compare is actually upper bounded by a constant, which kind of reduces your complexity. Is this clear? When we look at the code, it will become more clear. All I'm trying to say is that instead of comparing one with all other n points, say inside this band, I'm saying you don't have to compare with n. The number of points inside the band that you have to compare is not a function of n. In fact, it is a constant. Therefore, the n factor, right? The n that you have to do for scanning and sorting and everything, to that you don't have to add another n, because when you have to compare this point wise whatever there is in the inside band, it's only a constant number, and that does not add to the complexity like O of n squared or anything. Is this clear? Am I making sense?
Yes, ma'am.
Okay. Is this clear for everyone?
Yeah.
Okay. Okay, so we'll just quickly look at the code. Okay. If there are certain portions which you're not able to understand, you can just have a look at it and let me know later, because I would like to address the integer multiplication and the division tree also today, because otherwise the other two topics we will not be able to cover in the next call. Okay. So I'll just quickly go through the code. Let me know if you have any difficulty in understanding. So this is the pseudocode that we have. This is the pseudocode. That's So here you are actually taking the px and py, the list sorted in x via the x coordinate and the list sorted in y coordinate as input. You are checking if the number of points is less than 3. If that is the case, you will simply do compare all pairs, like 1 and 2 you compare, 2 and 3 you compare, 1 and 3 you compare, whatever is the shortest you give it, because you cannot do any better than that anyway. Now you consider the qx and qy, rx and ry as I have already explained here, and then you find the closest pair in qx, qy. This is Q1, Q2, and DQ is the delta 1 that I was talking about, right? The delta 1 we get from Q, and delta 2 is what the shortest distance you get from R, the part R. Now SY. SY is nothing but the points inside this band in this order. The points which are inside this band, which you have to compare, right? That is what I told you, no? Whatever are inside this band, when you're merging, you have to compare what is going across the red line, right? So whatever are the points inside this band is what you are going to get inside SY. And this you are constructing via QY, RY. As I told you, we are actually starting in the sorted order of Y, and we keep going from the shortest to the shortest y coordinate to the the smallest y coordinate to the largest y coordinate. So you do that, yeah, fine. Then scan SY, find S1, S2, D2. So how do I find S1, S2, D2? S1, S2, D2 you find by S1, S2, D2 is what you find by comparing this point with this, etc. Right? So you find the shortest distance, which is the DS. Now you return all these. And that is what is. So 1 minute, let me just see one thing. 1 minute, okay, just give me a second. So I'm a little lost as to what Q1, Q2 are. Can anyone help me out? What Q1, Q2 and R1, R2?
Yeah, ma'am. These are the point X, like X1, Y1, X2, Y2.
The point Q1 and Q2, right? Correct.
Yes,
got it.
yes.
Okay. Q1, Q2, connected by a distance DQ, right? Okay, got it. Thanks. Sorry, yeah. Okay. Got it, no? That you are returning the closest pair, not just the distance, I guess. You're returning the closest pair.
Ma'am, distance between this P and Q point we are returning.
That is DQ, right?
No,
the
ma'am.
method is
We are
returning.
calculating
Okay.
We make the method for calculating a distance, Euclidean distance. Returns the Euclidean distance between point P and Q.
Oh, okay. Sorry. Okay, so this is the shortest distance returned by the left subproblem. This is the right subproblem, is it? No, see, that is what it is returning, no? R1, R2, S1, S2. So Q1, Q2, DQ. Okay, so you have a problem here. Okay. So you have the P, you have divided into Q and R, right? Now, the Q and R have its own...
Okay, ma'am. You are talking of some other method. I was talking of this. Okay, sorry.
Okay. No, I got the point. So this is what you are getting from the Q part. This is what you're getting from the R part. And this is what you're getting from the S1, S2, DS, the middle band, this part.
Ma'am, in this line, Q1, Q2, comma DQ equals to closest pair QX, comma QY. Ma'am, here DQ is the distance between Q1 and Q2, and DQ is the closest pair between closest pair of QX and QY. This line is what I'm unable to understand.
No. So see what are you returning here? You are returning a 3 tuple, which is Q1, Q2, DQ, right?
Yes, ma'am.
That is what is coming into Q1, right?
So, ma'am, what is Q1 and Q2?
Yeah, that's what I started off with asking. So I'm
Ma'am,
yeah.
Yeah, ma'am, Q1 and
They
Q2
are points.
are the point
And DQ is the
the
distance between
the
them.
closest point in the Q side. I can say.
The closest, so Q1 and Q2 are the 2 points, the closest side, the Q side distant,
DQ
separated
is
by a
distance
distance
between them.
DQ.
Yeah.
Yes.
The first return statement is this. Closest pair and distance. Return closest pair and distance.
Q is the left side, R is the right side point.
So inside the QX and QY.
One second. Yeah. Okay, come, just 1 second. Okay, I'm just checking.
Okay.
Excuse me, ma'am. May I
Yeah.
add something?
Yeah, Adnan.
Yeah. So in the closest pair function, I believe that whatever we are returning is the minimum of these three tuples that we are returning, right? Depending on whether DQ is the smallest or that DR or the DS is smaller. So it should be min of these three tuples is what I believe.
Min of the 3 tuples, is it?
Yeah. So I think we are missing a min there. That is why we are only getting one of the tuples in the other call.
That is a single tuple. It is not 3 components of a tuple, right? Okay.
Exactly. So we should be taking the minimum based
Minimum
on the
of
distance.
okay.
So in this case, it will be the third component, I believe, of the tuple. DQ,
So here you have a min, but let me see whether.
We can't say that it will be the third tuple, but it will be based on DQ, DR, DS.
Yeah, that third component is what I said.
Yes.
Yeah.
Okay, so what you're missing is a min here, right? That's what.
Yes. Because of course we are only taking one of the tuples out,
Got
so
it.
it cannot be that we
Yeah.
are returning 3 and getting only one. That is not possible.
Got it.
This S1, S2, DS is between the two partitions, joining between the two.
That's correct. So you look at the left side, you look at the right side, look at whatever are crossing the partition. You get the minimum of the 3, and that is what you're getting here.
Oh yeah, minimum of the right hand or the left hand, or the minimum which is crossing.
Correct.
Right.
So, ma'am, here in this closest pair QX and QY, you mean here Q is divided into two partitions, QX and QY, and Q1 is Q1 is.
No. So again, you're getting it wrong. No, QX and QY are not partitioned, right?
Yeah. Okay. So Q1 and Q2 are in QX, QY. Is this something? And DQ is the smallest distance between them.
Q1 and Q2 are from the left part, correct?
Q.
Yeah, the small. So
Q,
the
right?
Q itself, you are actually separating into left, right, and middle part, right? Whatever you're getting from that is coming to Q1, Q2, DQ.
Okay, so Q1, Q2, DQ are DQ is the distance in the QA partition, and the points are Q1 and Q2.
1 second, let us just see it as a picture here. See, you have a.
So excuse me, ma'am. There's one more thing that I'm able to see here is that the second tuple that we're returning, line number 10, that should, I believe, be DR and not QR, is what I believe, because that is the
this is DR. This is a typo.
Yeah, that's a type.
Yeah,
Because that is the distance between R1 and R2.
Yeah, this is a type.
Yeah. S1 and S2, so that is DS, and the first one is D.
Yeah, this is a pseudo code, right? So
Yeah.
it's not a run and tested code. So it's likely that, that's why this min is all missing possibly.
Exactly.
But this code, we would have run it, and if it is not working, we would have fixed it. But this is a pseudo code, right? So we would not have tried it. That's possibly the reason. Yeah.
Sure.
So what I was, yeah, sorry. Yeah. So what I was trying to say is this itself has a Q and R, right? Q dash and R dash, no? This has a Q double dash and R double dash, right? Is this correct?
Yes.
So whatever you're getting minimum from this, so there is an S also here, right? S dash also here, correct? So the minimum of this Q dash, S dash and R dash, right? That is going in as this Q. That is what you're getting, the minimum of this part. The closest pair call that you're invoking on QX, QY, right? That will go as this point Q1, Q2, QR, DQ. Then
Ma'am,
whatever
what is
you're invoking on, sorry?
What is S dash here?
S dash is the boundary, the overlapping area between. So Q, 1 second, I'll just show you. So you have the Q dash and R dash are like this, right?
Mm-hmm.
Now you have an S here also, S dash. That SY I told you about, right?
So
See,
S
this
dash.
this is the S. This is the SY, right? This is what I was talking about. No?
Okay.
The points which are there in this band, which are crossing across this middle line, that is the S. So
Okay.
whatever is coming from the delta, which is coming from delta 1 coming from here, delta 2 coming from here, and some delta dash which is coming from the middle, you're taking the minimum of delta dash, delta 1 and delta 2, which is the minimum distance in for the full problem.
Delta 1 is the distance in the left side. Delta 2 is the distance, minimum distance in the right side. And
Yeah.
delta dash are the minimum distance across the two.
Correct.
Okay. Understood.
So that is
And
what
we are
we are
taking we are taking minimum of all these three. So
Correct.
then we get the closest
Correct.
pair.
Correct. So for the Q side, right? So when you invoke this one, you are invoking it on the Q part, and which is returning the minimum of the Q1, Q2, R1, R2, S1, S2. That is this Q dash, S dash, and R dash. That is coming to the Q here, which is shown here. You can see this Q1, Q2, DQ, right? This is what's going. Again, for this Q double dash also, you have an S double dash, right? So minimum of Q double dash, comma, S double dash, comma, R double dash, right? That is actually coming to this R1, R2, and D. Is this clear?
Yes, ma'am. Now it's clear.
Okay. So can you do me a favor? Can you go through the code and let me know if you have any issue? Can I go to the next problem? This is straightforward application.
I have a problem.
Yeah,
with
yeah,
this.
yeah.
So I don't understand this thing, ma'am. The SY part.
SY here. This one?
Yeah. This 30
one?
From 31 lines.
31 to 36, huh?
Yes, ma'am. So here, what we are doing in the for loop, that this thing I understood that we are taking the py points because we are taking from down to up kind of thing, right? So why we are doing this comparison?
No, because we don't want to take anything outside delta, right? We are only taking the points within delta, no, from py.
Okay, only those points which are means XR is the minimum nearest one, right, ma'am?
No, 1 second. XR is this one.
Is the nearest point.
No, this one, right? This is the XR, no? What is XR?
Here it is XR is the point which is on the right side and it is the nearest one to the division. Yeah, this line, this red line. So why we are doing this kind of thing and why we are comparing it with the delta?
So let me just ask you. I want to get all the points inside this band from py. How will I do that?
I have to what I have to do. So okay, I have to compare every point. So why we are not taking the QY? Why we are taking PY? This is also my question.
So then you have to take the QY, then you have to take the RY. Both you have to take, no? Both are anyway available in PY.
Ma'am, can you just once check what is XR? Because XR, I can, from 20th line, I can see that it is the minimum X value in RX. Here, minimum means
it is. What is RX? RX is this part, no? What is the minimum value of RX?
Yeah, RX is the right part. Yes, you are correct.
So minimum value is this boundary, right?
Minimum value is no, ma'am. It is the minimum X value in RX.
Correct.
So the nearest point to the Rx, it is Rx 0, 0. It is saying, right? So it is the nearest point to this boundary, right boundary, but it is in the right side, right? So this is how it is saying. So
No,
my
I did not
question is, why
understand
we
your
are not
confusion.
taking QY then?
Sorry, no, I did not understand your confusion. See, I will tell you, I'll just try to explain once. Okay, so what they're saying is the minimum value in the Rx side. So this is the Rx side. So if you have, say, your so just like we have defined for QX, right? We defined for, say, Rx also. I don't remember the figure and everything's kind of gone. So I don't know. So suppose 3, 4 and 4, 3, 4 and 4, 4.5 are the points in Rx. Okay. If this is the case, you take 3 as the XR. So something like you are taking 3 itself as here, right? This 3. This will be the 3x. Here x equal to 3 will be the point here.
3, 4 and 4, 5 we have the point, right?
Yeah.
So XR will be 4, right, ma'am?
Oh, sorry. Correct.
In the right direction, yeah.
1 second. No, the one with the smallest y, but you will take the x coordinate of that, right?
Yes, X coordinate.
Smallest. Okay, 1 second. Let me see whether the problem. So for me, I feel it is clear. I'm still not able to understand what the confusion is. Let me try explaining it again. So you have Rx, which is a set of all points in R, which is sorted in order of x coordinate. Correct? You take the first point. I mean, you take that first point, right?
First point and the exit value of this means, right? The exit
X
point.
coordinate of that.
X coordinate of it.
Correct.
So X is that value.
Yeah, so that will be x equal to 3 only. Yeah. Okay. So now what is the confusion?
Yeah. So here in the 31st, this 35th line, what we are doing, we are taking the x coordinate of every point in py,
correct. Okay.
And then we are subtracting the xr distance.
So is this a x coordinate?
Which
yeah,
one?
it's the x coordinate, right? Correct. Yeah,
Yeah,
that's
x
correct.
coordinate.
Yeah.
The x coordinate of p point, right? And then we are subtracting xr.
Correct.
And then we are comparing it with delta. If we are having, if the distance is less than delta or equal to delta, we are keeping it in sy.
Yeah.
Ma'am, why we are doing it for py? Why we are not doing for qy? That is my question. First question.
So sy has points from both sides, right?
This py will be having the points.
This is the q. This is q. This is r, right? So sy has points from both sides.
Yeah. So anyway,
I want to take only those points. So how do I say that I want to find the delta from this point? How do I define this point? How do I want to find the delta from this point? So I'm just saying that the minimum of x, let it be the one that is a partitioning line. Minimum of the r part, that is a partitioning line. Whatever is a distance delta from here, I will put into y. Whatever is a distance delta from here, I will put into y. And that has to be done for both q and r, and hence I take it from p.
Okay, ma'am. The another thing is why we are doing it with xr only, means
no, that is because the delta distance is computed with respect to the x-axis. Sorry, the y-axis. The distance is on the x-axis, right? The distance delta is on the x-axis that we are considering, right?
Yes.
That's why we are subtracting the x-coordinate only.
Okay.
So the point could be anywhere here. Y-coordinate could be anything. But the distance from x, this is delta. That is what I'm saying.
Yeah,
for that I subtracted the x-coordinate.
Okay, ma'am. Okay.
Yeah. And the one other thing that you have to see here, it is, see, this is different. But here is where that constant factor is coming down. You can see that, right?
Yeah, so ma'am, here we are just comparing the adjacent point, right? The SY0, SY1 means in 41 line, we are just comparing the next
No, we are
point.
comparing. See, this is from I and this is j plus 1.
Yeah.
So you're actually taking that 1 and you're comparing with 2 to 16.
Okay. Yes. Okay, ma'am.
So, and you're saying either 2 to 16 or only as many points are there.
Okay.
Whichever is the maximum, you do it only till that.
Okay. This is very complicated algorithm. Yes. Okay.
So see, the best way to learn these algorithms is take an example which will cover all these scenarios and then do a hand running. Instead of just writing the code and taking it, just and understanding algorithms, you just have to do a hand running, take an example which will likely cover all scenarios so that go through all the for loops, if parts, everything, and then you'll be able to understand this better. Okay. Yeah, so again,
Excuse me, ma'am. One question may I ask?
Yeah.
So in line number 43, we have this minimum, I plus 15. So is that 15 a kind of a general constant that we'll always have no matter what situation we are in? Is it like a general?
Yeah, that is what we explained using that squares and all that. 16 squares.
Okay, so it is like kind of proven, right? I mean, just wanted to confirm.
Yeah. Otherwise, see, what we would
Yeah.
have to do is we would have to scan through something like
everything.
If you had simply put it as size S, right? It could be as bad as n. That's the idea.
Right.
Then both for loops are of complexity n, and you get an O of n squared. But here you are bounding it 15 comma n, whichever is minimum. Not n really, the number of the size of sy, right? So you're bounding it by 15. You cannot go beyond that. And 15 being a constant, that for loop has a constant complexity.
All right. So that 15 is like fixed for every kind of
exactly.
problem.
That is the beauty of the algorithm. See, algorithms typically could be, I mean, because you are using this O, right? You can very well say that this O of n squared also. Anything which is O of n log n is also O of n squared, right?
Right.
But what you want to show is a better bound. And these kind of analysis is what gives such beautiful results. See, there are so many randomization techniques also, which will enable you to calculate the expected running time, right? That is over all possible inputs and all this. So there are certain analysis that way which are like really beautiful. In a single, I mean, if you look at just at the for loops and the code and everything, you would not be able to find that. But otherwise it can be like really interesting. You can bring down the complexity by doing some kind of finer analysis and
Right. So had it not been the case, then as you said that it will be like O of n squared only.
Right, because we don't know what the size S is, right?
Exactly.
But here we are bounding it by 15. You cannot be more than 15.
Correct.
The sizes can be less than 15, then you only run it so many times. If it's more than 15, I don't want to do that. I'm only going to run it for 15.
So, will it be fair to say that the analysis that we just performed has kind of proven to us that it will not go beyond 15, and then we have
that's what correct. And that is why we have written this code. The 15 came because otherwise what we would have done is simply for I in range 1 to n. For I in range 1 to n, we would have compared all the pairs.
So the solution space in some sense got shrunk, right?
Yeah, so the design of the algorithm is in a way related to the designing of, I mean, you look at the problem in more detail and you try to see whether you can have some kind of an optimization where you can bound by a constant value.
Right.
It doesn't have to be, I mean, it may not be possible in all cases, but in certain cases like this, you are able to clearly see that cannot go beyond 15. So you bound by that and you say that, okay, I have a constant complexity.
All right. Sure. Thank you. It's clear.
Okay. So please try out this. There is nothing more than what we have explained here. There may be few subtle things which like we discussed here, no, the absolute value of, so the absolute value is also should be clear to you. Whatever goes to the right side, whatever goes to the left side, you only want the absolute distance. You don't want the negative value for that, and that's why you're actually taking the absolute. So these kind of small things might be there here and there, which you can try to figure out. If there is a problem, please ask in the next session. Okay. Okay, now
Can you
comes the
explain this? Yes,
sorry.
y of 0, I couldn't understand that.
Sorry.
41. What is it? Sy of 0, comma sy of 1? I'm not getting that.
You're just starting with some minimum value, right? Because you want to have some
Yeah.
standard. I mean, anything you want to do, you kind of start off with some minimum value, right? So
Okay.
just to initialize something. Yeah.
Okay.
Okay. So sorry to rush through this, but I want to cover at least this and possibly the trees also, but let us see. Okay. So now this integer multiplication. Okay. So let us try this one example where you have say 1000. So something similar to, I don't know if sir has taken this, but yeah. You want to multiply these two values. How do we use divide and conquer for this, right? How can you even think about divide and conquer for simple multiplication? So let us look at another way of writing this. Say you have 12 into 100 plus 34, which is this value, whole multiplied by 87 into 100 plus 65. Is this okay? Let me know if you're not able to understand. These are simple arithmetic. I'm just writing it, just so that we can go ahead. Okay. Now you have 12 into 10 power 2 plus 34. There's nothing. I'm just rewriting it. That's it. 87 into 10 power 2 plus 60. Right? This is equal to 12 into 87 into 10 power 4. Multiplying these two plus 34 into 87 into 10 power 2 plus 12 into 65 into 10 power 2 plus 34 into 65. I have 1 multiplication, 2 multiplication, 3 multiplication and 4 multiplication to do to compute this if I'm doing a divide and conquer. So I'm going to do a divide and conquer where I'm going to write, bringing it into simpler value. See, this is a, okay, so one thing that you have to be clear here is what is n? N is the number of digits in the multiplier and the multiplicand. So here it is a n equal to 4. Okay. So depending on the number of digits in this multiplicand and multiplier, the time to perform this multiplication will increase or decrease, right? So what we are trying to do is we are trying to say, okay, there is an n by n into n digit by n digit multiplication. I'm going to divide into n by 2, n by 2, n by 2 multiplication. Can I do any better as compared to what the time I'm taking for n by n? So typical n by n will, what will do, you have to do 1334 into 5, right? Then 1334 into 6, 1 2 3 4 into 7, 1 2 3 4 into 8. All these things you have to do, and then you shift by 1, you shift by 2, you shift by 3. Okay, I hope I'm making sense.
This code, ma'am, we are assuming that both x and y have to be of the same length, can't be of different.
Yeah, I mean, this is the worst case possible. If we have something smaller, then you would still consider that this is n equal to 4. Whatever is the largest, you would consider that as n. Okay, so you have whatever is the product of 1 2 3 4, you will write it here. Whatever is the product of 1 2 3 4 into 6, you will write it here with 1 digit shift, right? Then you write it here with 1 digit shift, you write it here with 1 digit shift. So you are still doing 4 multiplications here, right? Now we are trying to see if we can do any better by using a divide and conquer. So you have brought it to some form like this. So here again we have 4 multiplications, right? So with respect to 10 power 4, 10 power 2, 10 power 2, don't worry about it because it's just adding zeros and shifting the digits, especially when it comes to binary.
There will be 4 multiplications into the number of times, the length of n. 4 into 4.
Sorry, how was that?
So here what you
this
have
is
said.
one multiplication. This is one multiplication.
Okay.
Number
5,
of multiplications
6,
is what I'm talking about.
6. Right. Okay.
Okay. So, so shifting, I will come to that later. But before that, let me just conclude this part of it. So, one second. Okay. What I'm trying to say is that this multiplication, right? This you can ignore for now. because multiplying by these factors are just simply shifting the values to the left inside the registers of the CPU, which I'll show it to you later. But here you just look at this. Okay? Now I'm going to tell something which is totally unrelated. Okay? 1, 2, 3, 4 into 8, 7, 6, 5. Let us call this as x1, this is x0. So this number is x and this number is y. This is y1 and this is y0. I'm going to say that I'm going to do something like x1 plus x0. Right? This is this will seem like it is totally unrelated, but I'll tell you what I'm arriving at. This is equal to x1 y1 plus x0 y1 plus x1 y0 plus x0 y0. Okay. So as you can see, this is my x1, x0, y1, y0. This is my x1, y1, x0, y1, x1, y0, x0, y0. Okay. So I'm actually multiplying this is again x1, y1 into 10 power 4 plus x0, y1 into 10 power 10 squared plus x1, y0 into 10 squared plus x0, y0. So this is actually comparable, right? Here you have a 10 power 4 here. Here you have a 10 power 2. Here you have a 10 power 2. Here you have nothing. So that is what this and this are comparable. Okay, but you cannot still get the value. You still have 4 multiplications. So how can you do any better? This involves a single multiplication, right? You have x1 plus x0 into y1 plus y0 is a single multiplication. Now, if I put it as x1 plus x0 into y1 plus y0 minus this part and this part, I'm going to bring it to the left side. So x1 y1 plus x0 y0 is equal to x1 y1 plus x0 y1 plus x1 y0. Is this rearrangement clear? I'm just having this one and I'm bringing this and this to the left hand side. So I have only what is the
But we are ignoring the 10 to the powers.
Yeah. I mean, it is not related to this at all. I'm just trying to trying to simplify this. I'll come to that now. Okay. Now look at the 12 into 87. Okay. What did I write here? This is x1 y1, right? x1 y1 into 10 power 4 plus x0 y1 into 10 squared plus x1 y0 into 10 squared plus x0 y0 is equal to x1 y1 into 10 power 4 plus x0 y1 plus x1 y0 into 10 squared plus x0 y0. 1, 2, 3, 4 multiplications. Here you have 1 multiplication, 2 multiplication and 3 multiplication. Now you can put this whole value in place of this one here. You have already computed this value for this one. So 1 multiplication. You have computed this value for this. So 2 multiplication. Now instead of doing this multiplication and this multiplication, you will do 1 additional multiplication of this minus the sum of the multiplication which you have already done, which is this whole factor you will replace here. So you do 1 multiplication for this, 1 multiplication for this, and 1 multiplication for this. So eventually you are reducing the number of multiplications from 4 to 3. Is this clear? Are you able to relate it? No?
Okay, since we have done x0, y0 and x1, y1 beforehand, So in this minus x1 y1 plus x0 y0 is not counted because we've already done that.
Correct. This is already done.
And the other side, that x1 plus x0 and y1 plus y0 is one multiplication.
Correct.
Right. And right. Okay.
How
So
about
1
others?
and
Yeah.
2, 3.
Yeah.
3 multiplications.
Yeah, you got it. No? You got the point.
Ma'am,
right?
one doubt I have: x1 plus x0 into y1 plus y0 is the main thing which we require to do. Again, we are calculating in the middle term. That why it is coming again? No?
No, I did not understand. What is it?
In multiplication, we have bifurcated into x1 plus x0 into y1 plus y0.
No. This multiplication we have not bifurcated into this. That is not correct, no? How can we do that? See, this is not equal to this. This and this are not equal. This is not that is not the divide and conquer I'm talking about. The divide and conquer I'm talking about is the 4 digit you are dividing into n by 2 multiplication. See, this n by 2 n by 2. You are actually dividing a 4 digit number multiplication into 2 n by 2 multiplications, and number of multiplications which you would have had to do by that n by 2 multiplication, you are reducing from 4 to 3. I will show you how that analysis helps. Sorry, how that helps in the analysis.
But ma'am, actually it's not 4 to 3. 4 to 3, yeah, in the example you're given, but if we include the 10 to the powers, then it'll be more. But it'll still be less with the substitution.
No, I did not understand. What is it? 4 to 3
So
will not be less.
No, if you come down, just roll down. Scroll down.
Mm.
Yeah. So this, we are also multiplying by 10 to the
This
power of
one's-
4 and
Yeah, this is what I wanted to come to. So suppose instead of 10 power 4, okay, so in computers how it is all done is using binary, right? So instead of 10 power 4, so this is 4 is what our n, right? So instead
Right.
of 10 we have 2 power n, right?
Right.
Now if you want to multiply something by say some power of 2, say suppose you have, do you know binary representations? May not be, right? Okay. So for
Yeah,
binary
yeah.
representation, say I'll just show you with just 4 numbers. Okay. So this is the binary representation. So please correct me if I'm making any mistake. Okay. 0, 0, 1, 1. So how these are coming also, I'll briefly explain so that you can appreciate that. Okay. 0, 1. Okay. Now this digit we say it's for 2 power 0. This is 2 power 1. This is 2 power 2. This is 2 power 3. This first digit is 2 power 0 stands for 2 power 0. So what it means is that, say suppose you take 3. This digit, like how do you compute say 1234 in decimal? This is 1000, right? Which is 1 into 10 power 3 plus 2 into 10 power 2 plus 3 into 10 power 1 plus 4 into 10 power 0. This is what 1234 is. This is 1000 plus this is 200 plus this is 30 plus this is 4. That is what is giving you 1234, right? Just like that, in the case of binary numbers, say 3 you have, right? So 0 into 2 power 3 plus 0 into 2 power 2 plus 1 into 2 power 1 plus 1 into 2 power 0 is equal to, this is 0 plus 0 plus 1 into 2 power 1 is 2 plus 1 into 2 power 0, this is 1. This is equal to 3. This is the decimal value that we have. So 0011 represents the number 3 in binary representation, and how we compute the decimal value is we actually multiply it just like we do for the decimal, right? We multiply it like this and we get the decimal value. All I'm saying is 0011 here, 0011 represents 3 in binary representation. Just take it for granted for now. Those who are not aware of binary representation, you can just go back and refer in case you need to. Otherwise, you can just forget it also. That's okay. The point is, you have 4 here, right? This is 0, 1, 0, 0, because this is 2 power 2. 8 on the other hand is this. Now you look at a CPU register. It has all these binary representations, right? So you had 4 here initially. Now you want to multiply it. What do? You want to multiply it by 2. What do? You just shift it one digit, no? You just shift it one digit and fill it this with a 0. This is the binary representation of 4 and this is the binary representation of 8. The point that I'm trying to say is the multiplication by 2 power n in the case of machines is only shifting in the CPU registers. It is not actual multiplication. Somebody
Right,
was
right.
asking about multiplication taking time, right? I mean, the 10 power 4 is an additional multiplication, right? So I'm trying to say that it is not, in fact, a multiplication in the binary representation. It is only shifting this one to the left when you want to double something.
Clear, ma'am. Clear.
Okay. See, see, in the case of 3 also, you see 3 is 0, 1, 1, right? 0, 0, 1, 1. See, what is double of 3? You have shifted it one digit and you've added a 0 at the right hand side.
Right.
Got it? Yeah. So,
Right.
so this is all what I'm just trying to say is that it is only shifting to the left. If you want to divide, you shift it to the right. If you want to, so there are all like corner cases where there are floating point numbers involved and everything. There are corner cases, but I'm trying to tell you in general, multiplication means you shift one digit to the left. The whole number you shift to the left and you add a 0 at the end and that becomes a double the number. If you want to divide it, you shift it to the right. Okay. Yeah. So this you do not have to consider as a multiplication is what I'm saying. Okay, that's the point. Now, let us do the analysis. I'll try and explain. Okay. So this 1, 2, 3, 4 into 8, 7, 6, 5, right? So this is n and n. This I'm going to divide into 4 multiplications by the other count, like 12 into 87, 34 into 87, 12 into 65, and 34 into 65, right? This was my naive approach, the 4 multiplications that I was doing, right? Now these are all like n by 2 into n by 2, right? So I have, how will my recurrence look like? The recurrence will look like d of n equal to, how many subproblems do I have? 4, each of size n by 2, plus for each multiplication you have an O of n, sorry, not O of n, n. So n. Yeah, so if you have to do 12 into 87, right? So, yeah, okay. So here what you're doing is this number, this is 1, this is 2. So whatever is the size of this one, so that is the O of n. That is where the O of n is coming from for this part of the addition. You have to list this. No, one second. That's not correct.
Excuse me, ma'am. I have one question. May I ask?
Yeah.
So in the code, we are saying that the base case is given as when n is equal to 1, right? So I believe that we'll keep on breaking that digits, right, until we have 1 only, right? So should kind of not 12 into 87, rather it should be like 1 into 8 and 2 into 7, like that, right? Because we have to go till it is 1, right? Only one digit is there.
Yes, correct. The recursion will go till you reach the base case.
Right.
I'm trying to show you that there are 4 subproblems for each level is what I was trying to say.
Okay. But in the actual recursion, I believe we will go until the digit is only 1, when n is 1, right? 1 only. that is in the code also.
Yeah,
If
that
you,
is the basic step, right? That is, you cannot bring it down
yeah,
any
yeah,
further.
yeah,
You go
yeah.
till there.
That
Correct.
is the
Yeah,
base case.
and
So
n
that
will
is
be
like,
1. Correct.
yeah. So that we are assuming to be O of 1, right? That is constant for one single digit.
One single digit will be constant. That's correct. So T of 1 will be 1. Yeah.
Yeah, sure, sure. Okay, thank you.
Okay. So, yeah. Okay. So, for now, let us just take it for granted that this is n. I will just figure out, this n part. Let me just check the lectures. I think that might be better.
N will be the length of the digit, right, ma'am?
That's what I'm a little confused with. In one second. So adding each partial product to cumulative sum is O of n. Okay. N partial products. Adding each. Just one second. Okay, so this is the combining partial products require adding additional O of n bit numbers. This is the O of n. So that's what I just mentioned. So I got a bit. So if you have, say at this level, so you have the partial products which are coming in between, right? This one. So what you do, so if you have say many levels like this, so first you add these two, then you add to that, then you add to that, then you, rather than adding all these together, how you do is these are the partial products. This is the first one. Second one, you keep adding, that will be an O of n. Okay, so that is what this computation, this multiplication, right? Whatever, I mean, you are going from this to this, that will be taken care of in the subproblem. That is the subproblem for 12. Okay, so the worst case scenario is when you have, okay, just forget about it. Okay, so we'll do an analysis here. We just go by solving this recurrence, which is, okay, you substitute the T of n by 2 by 4 of, so this doesn't have to be 4, this can be less than that, but this is kind of our upper bound, right? So here again you have n power 4 plus this n you will substitute as n by 2 plus n, right? This is equal to again 4 square. This 4 again square. Then you have T of n by 8 plus n by 4 plus n by 2 plus n. Okay. So you get the
Maybe
pattern.
4 into.
Sorry?
4 into
The whole.
40. No, 40 n by 8.
Outside the
This one 40, right?
Right.
This is what you mean, right? Okay. Yeah.
Yes, ma'am.
So,
Yes.
so that will be 4 cube. Yeah. So you have 4 cube. One second. Just give me a minute. Something wrong? Am I doing something wrong? Is this correct or? I did something wrong. Okay, that's fine. So that 1 4 is getting cancelled. That's what is happening. Okay. 7 by 2 squared. Okay, can you do this analysis offline? Okay, I will explain it from here. That maybe better. I write it, I mess up, and I will have to go back again. Okay. So this Tn by 2, I'm going to substitute with this, where n by 2 is substituted by again n by 4, and then you have an n by 2 factor. Now you're taking the 4 outside, but because you're taking the 4 outside, this 4 and this 2 gets cancelled, and you have a 2 here, 2 factor here, right? So this 2 plus this 1 along with it gets added here. Now you substitute again with this t n by 4. You replace it with 4t n by 8 plus n by 4. And then you again take the 4 outside and just this 2 factor, the 2 power 2 4 you have. So 8 you have here, you cancel it and you get another 4 here, because you have 4 into 4 into 4. 64 by 4 extinguisher. Okay, please just try to figure it out. I'm sure it is coming. I'm not completing. So I believe it is quite straightforward. Okay, it's just simple arithmetic. You just have to figure. Only the last step you have to be little. I'll just explain that alone. So this will be something like 4 per k t of n by 2 per k plus 2 per. So here, as you can see, when you have 4 squared here, it is 2 power 1, right? 4 cube you have here, it is 2 power 2. So you have k here, this will be k minus 1, right? So this is k minus 1 plus etc. plus 2 power 0 into n. So now this will go to the base case, so it will be 2 power k equal to 1. So k equal to log n. You put that in this whole equation and this is what you are getting, right? Now 4 per log n, right? This you can write it as so a per log b, you can actually write it as b per log a, right? Is it correct? Anybody knows? Okay, let me try to figure it out. 4 per log n. So you can actually write it as log n is equal to 0. Put the log on both sides. So log n into log 4 equal to log z. So this is, now you put it as log 4 into log n equal to log z. So this is equal to log n power log 4 is equal to log z is equal to n power log 4 equal to log z, which is n power, sorry, this log I'm taking from both sides, so z equal to n square. Is everyone okay with 4 per log n equal to n per log 4? Is everyone clear on this?
Yes, ma'am.
Okay. Yeah. So you will get it as O of n squared. So that's what you're getting as O of n squared. So just try to figure out these steps. Okay. I mean, it is straightforward, but so with brackets, I'll really mess it up if I do it. Okay. Okay. Yeah. So yeah. So now the idea is like you have a O of n squared algorithm, right? And that is coming because of this 4 factor. What we are trying to do is we are trying to bring it to something like this, t of n by 2 plus n. This will actually reduce the, so here we had n power log n, right, which log 4. Instead of that we have n power log 3. So here you have seen that we have got this n power log 4, right, because the 4 is coming from that subproblems 4. So instead you will have an n power log 3 here, right? So yeah, so that's what I was trying to say. With 4 multiplications, you have this complexities which is n squared, and you are bringing it to something we call it as a subquadratic. Okay, this is quadratic complexity, whatever we get it, but this is subquadratic. This is strictly less than n squared, right? So by using that simple formula, which seemingly doesn't have any relation to what we were starting off with, right? You cannot in general figure out the product of these two numbers, that 1334 and 8765, using this. I mean, there is no way you could have done it. This seems totally unrelated until you see that, okay, this term can be replaced using this full term, which will reduce the number of multiplications from this to this. So using divider, so where is the divide and conquer coming? You're actually dividing into 4 subproblems. You reduce the number of subproblems and thereby you reduce the complexity using a clever method. So this algorithm was actually devised by somebody called Karatsuba. So sir actually narrates an interesting story also, or an incident also related to this. Please watch the lectures to find it out. Okay, so this idea is actually reducing. So you might think, okay, how does it really help from coming from power log 4 coming to log 3? When you have very large numbers, when you have to, in the case when, I can't imagine, but as n tends larger and larger, right? Log n and log 4 and log 3 can make considerable difference, right? So bringing in general in algorithmic complexity, if you're able to bring something from quadratic to subquadratic, linear to sublinear, these are all considered as achievements, because it's really involves some very tricky ways of analysis and some kind of.
I have one doubt, ma'am.
Yeah.
This the first step I've understood, but if you go scroll up, there is a recursion which is happening in the code. Above this scroll, here. So the first I've understood this x1 plus x0 times y1 plus y0. Now what will happen in the second recursion?
See, x0 in itself is 2-digit, no? Y1 is also 2-digit, right? So each of this will be computed using the
okay, so it will become x0 plus y1.
Yeah, something like that. Correct. Yeah.
Okay.
Correct. X0 plus y1. So x0, 0, whatever, not x0. So x0 has 2 components, right? x0, 0, sorry, x0, 1 and x0, 0, right? 2 digits here, right?
Right.
Yeah. So x0, 0 plus y0, 1 or something like that. You got it, no? So this will again happen.
Okay.
So that is what is reflecting in that recurrence, right? 4 into t of n by 2 becoming 4 into t of n by 4, right? So that's what.
So I just wanted to see from the digits what will happen, because here you've added 12 with the 34 plus the other multiplication number, which was 8,000 something. And so I wanted to know the next step. So the next step will be further adding them. Yeah, those two.
Adding the individual digits, correct. Just try it. I mean, maybe you can try it out, one simple example, and see whether it is actually working.
Right.
Okay. So the code is very simple. This is actually finding the so you're actually when you're actually dividing by 10. So you have say 1234, and you're dividing by 10. You're getting this. But when you're doing 10 power m, which is n by 2, so n is actually 4, right? So m equal to 2. So when you're dividing by 10 power 2, you are actually getting the 12, whatever we needed here, right? This 12. For then this one again, you take the remainder of that. Okay, so 1, 2, 3, 4. You again divide by 100, and you take the remainder. You get the 34 here. So you get the 12 here and 34 here. So this is the actual quotient, and this is the remainder that you're getting, which is you're splitting the 4-digit number into 2 2-digit numbers. Same way for the y also, you will split it into 2. I hope this part is clear, right?
Clear.
Yeah. Now you are getting that x1 plus x0, right? So this part, x1 plus x0, this is the xh plus xl you are doing. Then y1 plus y0 is this part. Then you are multiplying again you are recursively calling this method using this.
Okay. So here in this this xh, which is coming in fast multiply xh, again gets divided by 10 to the power of n, right? To get the
yes, yeah. So I mean, it is again recursive subproblem, right? So small.
Right. Got it. Yeah, got it, man. Right.
Okay, so again, you don't worry about this 10 into n because I say as I was just mentioning, right, the case of binary multiplication. So eventually, internally, this will all be binary multiplication. So don't worry about it. It will be just a left shift of this numbers. Okay, so just for so that's about this is like very straightforward. Only thing you have to understand is how you replace this with this. That's all there in this. That's all there in the crux of this algorithm, which simplifies the O of n power complexity to O of sorry n power 2 to n power log 3. Yeah. So yeah. So I have one more topic. I'm not sure I can take it today, which is this recursion tree. So I'll just conclude by saying something which is common to all the trees. See,
One more doubt in the previous one.
yeah.
So the basic this algo is just reducing it. The divide and conquer method is just reducing it by one step from 4 to 3 multiplications in a 4-digit multiplication.
See, divide and conquer can work even otherwise. Okay, even with this, with the other this step that we have right here, like you can split it into
Right.
two. That you can still do that, but a simple divide and conquer doesn't help. You have to use a more clever divide and conquer. That's the point. See, you
Okay.
can still
But
whatever you're doing is still a divide and conquer only, right?
right,
You can do it using that 4 multiplication also. You can have a divide and conquer, right?
right, right,
But you have to use
right.
a clever divide and conquer to achieve that 4 to 3
Okay,
reduction.
right.
Okay. So yeah, okay. So I'll just go ahead with some common conclusion which I wanted to do. So in the case of divide and conquer, as I was showing this, I mean all the places like we have been drawing. So this is nothing but a tree, right? This is a tree where you have this problem P1. You divide into subproblem 1 and subproblem 2, and then you have say subproblem subproblem 1 etc. Right? So as I told you, like these are disjoint, right? These do not have any common overlapping uh, components at all, and you combine the solution and everything. So instead of solving the recurrence like we did, right, the tedious way of doing the recurrence, can we find the complexity of this algorithm in a much simpler way? That's the question. So let us look at the simple case of binary search, right? You have this binary search, sorry. So binary search, you have say something like this. You have 6 and 12 here, and then you have say 2 and 7 here. Then you have say 11 and 14. Okay. So this is your binary search tree. I hope you're aware of binary search tree, right? Are you all aware of binary search trees?
Yes,
Yeah,
ma'am.
yeah.
Okay. Yeah, so this is some binary, some example binary search tree I've given. So you want to find out whether you have a value 11 in this. Okay. You come here, right? You come to this node, you see that okay, 11 is larger than that. You go here, you come here, right? So this is the tree. Now, the maximum that you have to traverse through this tree is what? The height of the tree, right?
Right.
Correct, no? The height of the tree. So, in the same case, if you are able to figure out, like you have divided into so many subproblems, say you have something which is n and you have divided into say n by 2, n by 2, n by 2. This again getting divided into n by 4, n by 4, another n by 4. So this way, if you can actually figure out the height of the tree, right, then you can actually get an easier I mean, in a shorter way, you can actually get the complexity of a divide and conquer problem. So this is something which is very interesting with respect to divide and conquer strategy only. Like greedy algorithms, you cannot do this kind of analysis. Here, because the subproblems are disjoint, see, if you had overlapping subproblems, then you are not very clear about this distinction. But if you are very clear about the subproblems being disjoint, then the height of the tree kind of gives you some indication. Of course, you have to know what is the effort that you're spending on each level. See, at this level, see, for instance, the binary search, you are only spending time on this node, you are not spending here. But if it was merge sort, you had some one big list here, shorter list here, then you're spending time on this one as well as this one. So at this level, what is the effort that you're spending? At this level, what is the effort you're spending? So here, in the case of binary search, you're just comparing. This is an O of 1 operation that you're doing at this level. And therefore, it is the height of the tree, which is the complexity. Whereas if you are spending, say, O of n here, and then you are doing this O of n at every step, that will be O of n log n. In merge, you can see that at every step you're doing O of n, and the height of the tree is log n, right? So you have this O of n log n. So I'll explain it in more detail later. I'm just trying to motivate you to think about it. It's that, it's much easier to compute the asymptotic complexity this way, but yes, it is not possible in every case again. But in general, for all the divide and so for instance, you have the quick sort, right? You have the quick sort in which we said that you have an n and you have an n by 3 and 2n by 3. So as you can see, the subproblem size is not same here. Still, you can figure out if you know what is the amount of work that goes into this level. And if that's the same amount of work that goes at every level, then you can actually multiply whatever is happening at each level into the height of the tree. That will be the total effort. The subproblems do not have to be of the same size. In the case of quick sort, we said, like, somehow if you are able to say that the median is coming somewhere between n by 3 and 2n by 3, right? The median, if whatever the pivot that we are choosing is between n by 3 and 2n by 3, then we get the O of n log n, right? So that actually we can get it from this if you are able to estimate the effort that goes at every level. So estimate that goes at every level to the height of the tree will eventually give you the complexity for the whole algorithm. So we'll go to that detail in the next session. Just wanted to briefly give you an idea about this. Or do you want to continue and you want to do this also? Or shall we do it in next session?
Next session, ma'am.
Okay. I think, yeah, okay. Okay then, sure. Anything else with respect to what we discussed today?
Ma'am, in closest pair, I just have some questions.
Yeah. Do you want me to share?
Yes.
One second. Yeah. Yeah.
Not this, ma'am. The code part. Can you share the code, ma'am?
Yeah.
So yeah. So in this we are just doing this comparison thing only 15 times, right, ma'am?
At most 15, yeah.
Yeah, at most 15, yes. And these 15 points are not in distance of delta by 2. That is what our idea is, right? Means the points are not coming within this delta by 2. Means these are belonging to different blocks here, right? The blocks
Sorry,
with
no, I did not understand. What is it? Different?
yeah. So I is the first point, right? Like if you give the number to these boxes.
Okay.
But these are not necessarily the numbering that you are giving. These points are not necessarily the same one. These can be anything, but these are 15 points above this ith point. Is that, ma'am? Okay, let me tell you once again what my question is.
1 second, let me just try to understand. Just give me a minute, okay? This one, I mean this. Distance between SY plus 1. Yeah. Okay, tell me, what is it?
Yeah. So, ma'am, here we are comparing
Yeah.
the I. Suppose 1. I is 1
Uh,
for the very first time.
uh,
Then we are comparing I with the 15 other points, 15
correct.
other points, right?
Correct. Yeah.
So these points are not necessarily the delta by 2, not the numbering, the same numbering that we have given. These can be anywhere, right? These are just the top points of that
Sorry.
top
Yeah, yeah.
15 points of I, means above the I, whatever the 15 points that we have. Is that we have numbered like 1, 2, 3, 4, 5, 6, 7, 8, like that
So
we have.
let me just ask you one thing. How is the numbers coming in SY? In what order have we added it to SY?
We didn't order in SY we are just giving the number. We are adding the points in
This one,
the
right?
way
Yeah.
that PY has stored in
Yeah.
the
What?
same
How
order.
does PY store it?
PY just stored according to this uh,
Increasing Y coordinate. No?
increasing Y coordinate order. Yes.
Yeah. So if I'm starting, say, from point 1 here,
Yes.
the next point will be something which has the next Y coordinate, right? Something here.
Yeah.
The next Y coordinate may be here. Next Y
Maybe
coordinate will
here
be
or
here. Maybe
can
here.
be
Yeah.
can
Maybe.
be can
Let
be
me just
anywhere.
number the squares. You can tell me. Yeah. Can be
Yeah.
anywhere, Mane?
Means I'm talking about 17th position,
No, it
not
cannot be
16th yet.
17. No. Why? See,
That is
if it
what
is
my question is.
17, then the size is, what is the size is?
Size
No.
is
Okay. Okay. So, okay.
length
So, no, no. One minute.
of
One minute.
SY.
Okay.
Yes.
Sorry.
Length of SY, size
So,
S.
what you mean by the, okay, so you have, say, I equal to 1. Okay. Correct. Now you are comparing J plus 1 with J plus 1, right?
Yes.
This is the distance, no? You're
Yeah.
calculating SYI and SYJ plus 1.
Yes.
I
Yes.
is starting from 1, so you suppose it is 1. Now J is starting from 1 to 1 plus 1, 1 plus 2, 1 plus 3, 1 plus 4, etc. Right? Till 150. Correct? Correct, no? So
Yes.
you're only looking at the next 15 points.
Yes.
That doesn't have to be these squares, but they will be within this distance. It cannot be 17, is what I'm saying. It will be
Uh,
within this distance, right?
that is what I am not able to understand, ma'am. How come this? How you can say that it is not 17? Because anyway we are comparing the 15 points, right?
Okay, okay, I get your point. Yeah, yeah,
We are
but
just
does it
comparing.
matter really? It can be any. So, okay, uh, okay. So let me ask you. So even if it is comparing with 17, you are still assured that it will never be less than delta, right?
Anyway, in the
It
end
will
we are
not. The
comparing.
min-ness will not get updated because if it is in 17.
Yes, anyway, in the end, means in 45th line, we are mentioning here that men should be minimum of delta or mens.
Yeah, yeah, so that's what I'm saying. So
That is
minimum.
taken care of, right? Of all this. If we are getting in min as the distance which is
Okay, let
greater
me
than
just ask
delta.
you. Let me just ask you one question. So what your question is, like 1, 2, 3, 4. Suppose these points are not there, right? These are not there. Then this loop will actually check here also, right? That's what you mean.
Yes,
Is it
yes,
correct?
yes. Yes, I want to ask this thing. Yes.
Yeah, that is correct.
That is
Because see,
just
it is
correct.
only looking at size of SY, minimum of size of this or that plus 15, right?
Yeah, it will be keep on matching the 15 points, right?
Correct. That's correct. That's correct. Yeah, you are right.
Means if we don't have these 2, 3, 4 till 16, we don't have,
That's
suppose.
correct. Yeah.
Yeah.
But what you have to understand is it is. Um, yeah. So it is it is not possible that the 17 will get into
Will
the
be
min s.
having yeah, distance less than greater than, sorry,
That's
less
correct.
than
It
this.
will still do that because it has to do 17 to, because it doesn't know whether the 17 comes within the delta or not, right? So
Yes,
it can
yes.
still do till 20 or whatever. It will do the next 15, but it has to do only till 15. That's it. You're right.
Yes.
That's correct.
Okay, ma'am. So another question is this:
Hmm.
why you are saying this will be having this n square complexity if we don't have this analysis?
So we are not analysis. Suppose we did not limit it to 15, right?
Yeah,
Suppose we limited to size S, and if all points were within this one, right? If it was all the endpoints were here, then
that
this
will
loop
not be
will
the
also.
case, na, ma'am. Because we that will not be the case that we will be having all the points in this window.
No, that is okay. But size of S, what will you upper bound it as?
Size of S, anyhow, it will be coming less than this n. That is what.
That is correct. But when you're doing the asymptotic analysis, what will
Okay.
you bound as size of SS? Size SS.
Okay, at the time of analysis, okay, that is, yeah. We
See,
can't bound this to any number. That
any
is,
number. But here you can clearly bound it, right?
yeah, here we can clearly
Here,
say that.
yeah, suppose this I plus 15 was not there, min of I, this was not there, then this is also sizes, this is also sizes, right?
Yes,
And you do not know whether size is, it can be less than or equal to n is all that you can say.
yes, yes.
If you do not say that you can give this constant factor upper bound, then you will say that this can be at most n, at most n. So it will be an O of n square, right? Am I making
Okay.
sense?
Means yes, ma'am. This is little confusing because we can't say that. Yeah, sizes we can say it is less than or equal to n, but it will
But
surely be less than n,
no,
right?
it will. But I mean, see, it will be less than n because of our n, because we learned that it is 15, right? So technically, we know that however the program runs, it will always give this constant, this complexity will be like bounded by the 15. But how do you show it in the complexity factor?
Okay. Okay.
See, even if you do not do that, if you compare with all the points here, right? Okay, no, hold on, just 1 second. So what I'm saying is, okay, so let me just ask you, why is it not possible that the S of xy can have all the endpoints?
Yes, so it won't be possible because we are dividing before taking this sy into consideration. What we are doing, we are recursively calling, and then we are dividing left and right portion. So anyhow, we are calculating some minimum distance by
No,
doing
no,
this.
hold on, 1 second. So this delta is only to this effect, no, to the x-axis.
Yeah. So
What
we
if you
can't.
have something like, so suppose your delta is something like 1 and you're going something like 10,000 in the y coordinate.
Yeah,
So you
10,000.
can have 10,000 points here, no? And if that is all the points that you have, not 10,000, you can have 5,000 points, right? Which will be like 2 delta. If you leave 2 delta between each point,
Yeah.
and size S will be 5,000.
Okay. Means we can add the boundary. We can have more number of points.
No, see, no, SY can still have n points or n by 2 points, is what I'm saying.
Okay, n by 2 it can have.
But
Yeah.
we limit it to 15 only because we realized by after looking at it that we only have to compare it with the nearest 15 things, 15 points.
Okay, ma'am. So it can have, suppose we can say that it can have n by 2 points in this delta window. So
Yeah.
again, uh, my question is that anyway we'll be matching this item again and again to the 15 points. The same thing we are doing, right?
No, I
Yeah.
did not understand. See, what you're saying is the case where we have not done this 15 here at all, right? You're saying it is, see, you said both are sizes and it is anyway strictly less than n is your claim.
Yeah,
Right? If we
size,
did not
you can
eventually
suppose
take,
that it is n by 2.
yeah,
So,
size of this is n by 2, suppose.
okay.
right? Is that what you mean?
Yeah. So if it is n by 2, so a
Yeah.
for loop, for the first for loop will be running n by 2 times,
Correct.
and the second for loop will be running for 15 times. Okay.
Why? Because you are now limiting it to 15. The case where you
Okay.
said you're removing the 15, it will still run to n by 2 is what I'm saying.
Okay. 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 Got it, ma'am. Yes. It will not run for n by 2 times. Yeah. So
It
we
will
will
only
be
run
having n square.
for
Okay.
15 or n by 2, whichever is smaller.
Okay. Yeah. Now it is clear. Thank you, ma'am.
Okay. Okay. Yeah. Fine. So I think we can drop off today. And like next week, we will take the other parts also. So, okay. So that we'll address next part. Okay. I'm just going to, yeah, stop the live stream.
Okay.
Thank
Thank
you,
you.
man.
Yeah, sure. Thank you.
Thank you.
Bye.